So why am I saying quad? People are talking about dual. There are only two ports. We have done this quad pole maybe 4 or 5 years ago. Okay. This is again 1 megahertz converter, GAN-based converter that we have designed for to interface ultra capacitor with the battery. Okay. And 1 megawatt totem pole converter. See the size. See the size. Who did it after all? Students. Okay. And the resource scholar, master student. This work was done by an MTech student. Okay. This is one resource scholar. This is by an MTech student. This is a project staff. Yeah. So about the electrical engineering, I told you average age of a faculty member at IIT Bombay is now uh, uh, could be maybe less than 40. That is true for even for electrical engineering department as well. Okay, 60% of them are below the age of 40. I'm telling you because you should seriously consider doing PhD at IIT Bombay. Uh, Once upon a time, like yeah, so scholars like Joshi had come here to do PhD. Um, Now that number is, and that's how I came to know. We were in the sense he was sitting in an adjacent lab and he used to come and chat with us, and a lot of things have learned from him. That number is dwindling now. Why? Almost each and every college has become a QIP center. Don't get me wrong, nothing against. It is like a frog in the well. Get out of your college, go to some other place, okay? See the culture, okay? Then go back and do something better there. If you continue to remain there, yes, maybe life may become relatively simple because you'll be staying with your family and you don't have to do a lot of other things. But remember, kuch paane ke liye kuch kona hai. Okay? So right, that's the reason I'm talking about electrical engineering department, IIT Bombay. Uh, we are now around maybe around 700. I have lost that number, maybe 700 or 800 faculty members in IIT Bombay. Electrical engineering, we are having around 70. And I said around 60 to 60% are below the age of 40, young and energetic. Yeah, focus, maybe around 30 million US dollars sponsored research in the last 5 years. This is our average. This is the average. There are high profile labs. Okay. Yeah, there is a significant increase in the research scholars, publication, and patents. When you see these products and when you see those state of the art labs, you'll say, yes, I would like to work there. And when you come and work, your outlook changes. And when it changes, when you go back, you try to do something different there in your college. So think about it seriously. Yeah. Our faculty members also having a startup. Okay. Some of them. So there are quite a few companies. The startup they have started here. Okay. This is again, as I told you, this is the most exciting period for an electrical engineer, especially conventional electrical engineer. Okay, the electrical engineering at IIT Bombay encompasses communications as well as electrical. Okay, but whereas in other colleges could be maybe when it's electrical, it is maybe power 50 hertz. Okay, power systems and machines maybe the area. So there are thoughts on Atmanirbhar Bharat. Okay. Power of interdisciplinary collaboration of power electronics. See the areas that are required to make an. When they get involved, I'll assure you that whatever that you're doing will be a success. Otherwise, yes, you may be able to supply, get a project, try to deliver. You may be able to deliver. You may be able to publish a paper, and at the end, it will collect dust in one corner. Okay. Yeah. So unless you do university industry collaboration, it cannot be possible for us to make an impact. Times are changing. Times are changing. Is no longer the deliverable is papers. It is something else. It is a product of TRL level. Okay. So industry-led, university-partnered, government-sponsored projects, and there are a lot of funds that are available. You may know better. Maybe you can find out. Now, these are the research centers at IIT Bombay. I'm talking about National Center for Photovoltaic Research, National Center of Excellence in Technology for Internal Security. It was started in 2015. 2015, maybe approximately 80 crores. It is, I'll talk about it, Indo-UK Center for Education and Research in Clean Energy. I'll just tell you. Current research in NCPR, it was started in 2010. I'll just tell you, prior to 2010, there was some activity. We were here at IIT Bombay. There was activity in power electronics, there was activity in battery, all are isolated. Okay. What happened in 2010? Yes, the solar mission was announced. We formed a team, maybe around 30 faculty members came together, and we made a proposal, 2010 to 2015. Okay, we have an international, we have an advisory committee, and renowned people from across the globe, US, UK, Germany, Israel, Singapore, inside Australia, and many from India. Annually they meet. In the third year, they said NCPR has become a leading center in the world. This is the center. This is the sentence that we are told. NCPR has become a leading center in the world which carries out research in the area of PV. How it became so possible? 2010, within a couple of 3 or 4 years or so. It is because of the team effort. Team effort. Okay. It's like, we have just proved the moral of the Panchatantra story. I'm from a village. I have heard the Panchatantra story in my school. Okay. That's what they say. Unity is strength. Something similar here. We joined, formed a team, and we tried to make a difference. And we could make. Yes, we are quite successful. It is not that a smooth journey. Okay. It was tough. But then in 2016, we got a phase 2 for 67.5 crores. Government of India gave 67.5 crores, but then in paper it is around 87.5 crores because IIT also contributed something in terms of faculty time. Now we are writing phase 3, and today it has become a one-stop shop. Any issues in PV, NCPR gets a call from Delhi. Okay. So these are the areas: solar cells, perovskite, storage. We have a state-of-the-art, of course, art facilities in all these areas. Okay. We have even in a lithium-ion battery, we have a state-of-the-art facility. The unique feature is, I was told that you can't slice a charged lithium-ion battery, whereas the battery that battery has been developed here. If you slice the charged lithium-ion battery, it catches fire. But then if you develop, or the battery that is developed at IIT Bombay, if you slice it, it will not catch fire. That's what I was told. Okay. How it is possible? Yes, we definitely, again, is another team effort. See, here is our research was targeted towards rural India. We wanted to make a difference because how we got motivated, maybe because of our rural background. We wanted to make a difference to the quality of life of people working in a rural area. So that's the reason we developed solar water pumps for a deep well. The tubular pump driven by PV. Okay, it was a permanent magnet motor, synchronous motor driven pump. Okay, using the solar energy, water is pumped and stored in the overhead tank. Okay, we also designed a BLDC motor for surface pump. Okay, and we have developed the inverters for rural India. What is the difference between the inverter for rural India and for urban India? Country like India requires multiple technologies. In a developed nations, there is no significant difference between the quality of life of a rural country and the urban. Whereas in India, There is a significant difference. The technology that is appropriate for urban, it may not be suitable for rural. Why? In rural India, it has to work. It has to be reliable. It need not be efficient. Don't get me wrong. Because if it does not work, neither the service engineer will go. Because, for one inverter, he has to go 30 to 40 kilometers and he'll say, Baba, no, it may not be economically viable. Whereas sitting in Mumbai, if I just leave the phone and the service engineer is here, and I also can, quote unquote, warn him also. If you don't come here, I'll go to the internet and I'll put in something on Facebook. So, lot of things we can do is sitting in the urban places, but it is not possible in rural India. So that's the reason we targeted the rural India to improve the quality of life. We developed this inverter, the one which was shown grid connected. We have developed 300 VA inverter, 300 VA inverter for rural household, okay? And the pumps. In addition, there are a lot of other things as well. Yeah. So these are the state-of-the-art labs. And another thing, another center was National Center for Technology for Internal Security. Okay. I'll not spend time here. We interact with the manufacturing industry, state police forces, and R&D labs. Our target is to address the technology innovations gap in security. Introduction, yeah. Wide renewable energy sources. Okay. I hope you can see this is the statement that was made. Global carbon emissions are set to jump by 1.5 billion tons this year. This is a dire warning that economic recovery from the COVID crisis is currently anything but sustainable for our climate. Okay. So one thing today, however powerful you may be, okay, you will not be able to face the nature's fury. See the disaster that happened in the US, okay, the recent typhoon in UK, even in India. I do not remember raining in the month of January. So, what could be the solution? Would be maybe reduce the carbon emission, maybe by use one of the ways, maybe is using PV, another one is power from PV, another one is maybe UV, and see life cycle emission using solar photovoltaic. That's what I said. The present is this is an exciting time for electrical engineer, PV and EV. Okay. You have to get excited. Only then you will get excited. You can excite the students. Otherwise, it's not possible. So that's the national mission. MBJ's target: 6.67 million scale hybrid and electric vehicles by 2020 onwards. Yeah, 400 million by 2030. What are the issues apart from developing a motor converter, batteries, mileage, and charging stations? Today I can go out and fill my petrol, whatever, the gasoline from standing in any queue. But in the electric vehicle, the batteries are different voltages. Okay. Another thing is, if I think of going from here to Ahmedabad, I can't be charging, halting to charge the batteries at 2-3 places. And again, charging time cannot be 1 hour or so. So you need to have a very fast charger. The power for the charging station could be, if it is a huge charging, could be in megawatts also. So it has to come from 11 kV grid. Okay, apart from motor and the converter. See the targets for PV. But India targets 450 gigawatts of installed in by 2030. Okay, 280 gigawatts overall percent from solar. Where are we at present? We are at 42 gigawatts. How do we achieve this magic figure? But one thing is for sure, in the sense, unless we give targets, we will not be able to working that. At least there's some pressure on us. When there is a target, we'll start working. Okay? So yes, young minds are required and do out of the box thinking. only then we may be able to make an impact. See the status of the renewable energy in India. Okay. Indian perspective on solar generation increases by 10.7% or so. Okay. And historical growth in energy over the years. See the difference in 2020. Okay. Solar, wind, and this is coal. There is no improve. There is, I doubt there is any investment that is happening in coal-based power plants. Coal-based power plants. Okay. PV is the way to go. Okay. Mainly because one of the advantages, maybe you can have your own microgrid. You can have your own small grid, or you can have a small generating station on your roof that is powered by solar. Of course, there could be a wind also, and if need be a biomass. So you can have a small microgrid there. Okay, that is most viable. I'm not making a grid and supplying to a small village. Is it viable or not? Because the issue will be there. Who is going to own that? Huh? Who is going to own it? Unless that model is, of course, there are. I was told that there are many microgrids in India, but I do not know the actual status of those microgrids. But as a fact, being an Indian, I know. Sorry. So instead of having a microgrid, maybe having your own generation in your own this one. Maybe when you say that I own it, you will take care. That's how I admire. This is my policy, but it need not be set by all. See, more towards renewables globally. Okay. Renewable power generation across the globe, and share of renewables and coal. Coal is steadily falling. Solar is steadily increasing. Okay. And see the solar. Wind, of course, more or less. In India, at least it is quote unquote saturated. So this is the renewable energy potential versus 230 target in India. So this is the target. Okay, from the renewables by 2030. This year was for a couple of years. It is given 2020, 22, 26, and to achieve this target, this should be in our generation or in percentages. So how do we achieve? Even if you are not able to achieve the target, but at least there should be some progress. Now, what is the role of power electronics in renewable energy sources? Yeah. If there are any questions, clarifications, I can take a question or two here before starting my the topic continuing. It's up to you all. Maybe there's a small break. You can take, others can, while answering the question, others can. Otherwise, I can continue, not a problem.
Any participants, please, you can interact with sir if you wish.
If you wish, I'll just give you 2 minutes.
Yes, sir. Participants, you can raise your hand. We will unmute. Someone has raised.
Yeah, good. Yeah, go ahead.
Yes, unmute Mr. Sen Kumar. Mr. Sen Kumar, you are unmuted. Now you can interact with sir. Mr. Sen Kumar, you can unmute. And Karthik.
जल्दी कर लीजिए भाई साहब, 1 मिनट हो गया. Yeah.
Karthik, you can ask question just by yes.
Yeah. Sir, am I audible?
Yeah, you are audible.
Yeah, sir, Fernandez, sir, very good morning, sir. I am from NIT Rourkela. In the last week, I have attended your session and I interacted with you also, sir. Sir, I have one doubt, sir, regarding that NCPRE center. In the last week also, I asked. You told to visit that center and to get exposure on grid-connected PV system. You told that to write a mail to you. So could you please tell me in detail about what is the approach I have to visit and learn about
you send me an email. I will write to you. Have you sent an email?
No, sir. Actually, I am thinking about that only. I visited that website also.
You send an email. What is that to think? You will get in touch with that. Okay, fine. Yeah. Sure. Yeah.
Okay. Okay, sir. Thank you.
Yes. Yeah.
Okay.
Yeah.
And Pratham Tiwari, you unmute and you can ask. Pratham Tiwari, you can unmute now. We have allowed your mic.
Sir, I am Vishwanath Tiwari, Pratham Tiwari, my child name, sir. Because ID से मैं login किया हुआ है. I am from भोपाल, sir.
हम बोलते जाइए.
जी सर. सर मेरा एक डाउट था सर. एक्चुअली मैं सर PhD कर रहा हूँ सर RGP भोपाल से. तो I have taken topic techno-economic investigation of standalone photovoltaic wind biomass hybrid renewable energy system for remote area. Sir, I want to know scope of renewable energy in this topic, sir.
वैसा अभी स्कोप हमने बोला है ना, इन द सेंस अभी बताएंगे, देखते रहिए अभी क्या है. You have to see the previous slide हमने दिखाया ना, see the target. अभी ये करना है.
जी सर.
अभी ये कैसा करना है, वही तो स्कोप रहेगा ना.
जी. तो सर इसमें
maybe okay fine. This will take it off there. Any other question? Yeah.
Okay, sir.
Maybe
anyone else from participants? Participants, you can raise your hand. We will unmute. I think so.
Over?
Yeah, sir.
Okay, yeah. Maybe I just gave so far. I gave an introduction. My emphasis on having out of the box thinking, and maybe how do we achieve the government to attain to reach these targets. Okay. Now, and the success stories of IIT Bombay by having building a team. Okay. Yeah, now let me concentrate on power electronics. What are the challenges that one can, what are the challenges of power electronics one faces in this area? Okay, now, yes, this is a power from renewables. You have to feed it to the grid. Grid requires 50 hertz, almost constant voltage V. Okay? Here, if it is solar, I'm concentrating on solar, output is DC. Now, and if it is wind, again, variable voltage and variable frequency. Grid requires fixed voltage, fixed frequency. And while feeding the power to the grid, there are, of course, a lot of issues. Harmonics, okay? The so-called power quality. You have to feed the power at unity power factor. The THD should be THD of the current that is feeding within the should be within the limits specified by the standards. Here, power may change depending upon the environmental condition, but then those power cannot be, in the sense you can't have step changes in power here. It might affect the grid performance. Now, who does all this? This is all being done by power electronics converter. Okay. I'm calling advanced power electronics converters. What are the features? It has to be high power density, easily controllable, it has to be reliable, and it should be able to communicate between generation side as well as from the grid side. Okay. See the renewable energy and load interface via power electronic converters. Okay, various loads that we have, day-to-day loads, okay? And if you have a AC bus, almost each and everything, every appliance, there is a power electronic converter. Okay? This could be one of the reasons that, to have a DC distribution. People are saying it is efficient. Of course, we at IIT Bombay, we started in 2011. Okay, we are the first ones to get into this area. We started saying that 48-volt DC could be reasonable voltage to distribute the power at a residential level. Okay, but then if you choose 48 volts, you need to find out what could be the maximum load one can feed at 48 volts, because DC now. It is the voltage drop is directly magnitude subtraction, unlike AC. Okay? So, if you are trying to work in DC in order to improve people, it has been said that overall efficiency of DC distribution is higher than AC, because we have DC here, or you have variable voltage, variable frequency that you have to convert it to DC. Now, why to convert it to AC? Then again convert it into DC. There are multiple conversions. Can't I use straight away to DC? Makes sense. Makes sense. That's the reason we started working in that area. Now, if at the generation side, if you see, okay, this AC side, we have battery as a backup. Again, a DC to AC converter. We have solar photovoltaics. We have power electronics, DC to AC. Of course, in between, we could have many conversion stages depending upon the power. Okay. Of course, I sort of solar photovoltaic, but then you can have solar thermal as well. Solar thermal. Okay. Yeah. If I have a wind here, yes, AC to DC, DC to AC, again feeding to the grid. So yeah, and fuel cells, electric vehicle, charging, discharging, and of course, people say power. So in both the directions. So if you see, power electronics is there in almost all products that you are handling, right from mobile to electric vehicle, everywhere. So, but then same power electronics concept also may be the same, okay? But then the converter of the same power rating, remember, same power rating, 1 kilowatt converter, you may use it for electric, for a refrigerator, sorry, not for air conditioner, but then that 1 kilowatt converter may not be suitable for electric vehicle, because power density may not be so important, for air conditioner, but it is very important for electric vehicle, okay? Or maybe aircraft or wherever. So that is the difference. That's the reason I said high power density, easily controllable, unreliable. These are the quality how to build in there. Okay. So here is the role of power electronics. So if it is there in each and every appliance, and if this has become so popular, what could be the reason? The reason is it has to be flexible, it has to be highly efficient, it has to be reliable. These are the features. And what is the role of power electronics in PV systems? See here, we have a grid, AC grid, one grid in India, quite stable. Okay, connected today, installed capacity could be maybe inching towards around maybe 380. Sorry. What are the important features the converter should have? Okay, see here, we are saying islanding protection as well. What is the islanding protection? Why it is so new? In the sense, islanding is there in Mumbai city, like Mumbai, when the grid fails, it is expected that Mumbai city will become an island. Okay, nothing new. Nothing new. It is a age-old concept. But then why it is so important for solar PV? Okay? We will see. So, and here is the feature the grid requires, and here are the features that are required at the photovoltaic side. Okay, of course, MPPT everybody knows, this is current monitoring and diagnostic, forecasting and prediction. Because yeah, one of the limitations of PV is it is not dispatchable. You can't dispatch, you can't predict because what could be the generation tomorrow. Okay? So gone are the days where power we can the generating plants or can generate and feed it to the grid. Now the tariff is continuously changing. Power is being traded. I don't want to talk more about it because it is not my area. So one of the reasons to make solar power bit more attractive is you should be able to accurately predict and forecast it. In other words, you have to make it dispatchable. Issues in high penetration. Now, what are the issues in high penetration in LV distribution grid? What are the issues in LV distribution grid and how do we address them? Because to achieve those figures, achieve the targets, one of the ways is to have rooftop solar PV. Having a multi-megawatt systems and distributing is one way. Okay. Now see the space that is required. Okay. Now another way to achieve this target is to have rooftop PV. But then rooftops are generally connected to the LV grid. So what are the issues? Quite different. LV grid and HV grid. What is the difference? The so-called the Q factor of LV grid and HV grid. LV grid is fairly quote unquote resistive, whereas HV is not so. So whatever the concept that are there for HV grid, many cannot be used directly to LV grid. You have to do certain changes. What are they? See here. High penetration interaction, electric power system now shifting from the concept of centralized power to distributed energy sources. Gone are the days power was generated in the rural areas and it is consumed in the urban centers. Okay. This is what is happening to Mumbai. Power coming from Mumbai has to come from Koina. There is another one is at Nagpur. I forget the place. There is a super thermal plant. Okay, power is received somewhere near Kalyan and be consumed there. Now, whereas it is moving towards distributed energy sources. Where are they connected? Distributed energy connected to the edge of the grid, far end at the LV side connected. Okay, so structural diversity and distribution grid poses even greater challenges. Okay. And inverter-based PV is fastest growing and most crucial technology in the massively deployed distributed energy sources. So unique challenges for high penetration connected LV grid are bidirectional power flow. Why? Now you are connected a solar rooftop, and if it is lightly loaded, power may flow back or flow back. That doesn't not happen in the conventional grid now. Okay, so it may so happen that you may have to relook into the protection issues. Voltage profile. Let's see what happens to the voltage profile when the system is lightly loaded and when there is a high PV penetration and low PV penetration. Okay, failure of anti-islanding. Why it is so important? Solar. What happens in a conventional system? the moment the system, there is a grid stripped, so what will happen? Either the remaining load will come on other generators, therefore they will slow down, and therefore the frequency changes. Whereas what happens in inverters? Inverters, the static, okay. Now, whether the grid is existing or not, what will happen? Solar, since it is there, so output of the solar cells the solar insolation is there, the inverter will continue to feed the power. So therefore, one of the important thing is the moment grid has failed, you may have to you'll have to isolate it from the grid and maybe feed the local load. You may have to feed the local load. How challenging it is, you see. What I mean is, see here. Grid has failed. So circuit breaker has to be open. Okay. There is solar generation. Can the system work? As of now, the moment grid fails, you have to shut down. Okay. You may be, of course, there is a need for the power generation. You may be sitting in darkness. It's a summer, extremely hot. You can use this energy, but you are not able to. In this case, why? That is because you cannot accurately predict the generation, nor you can accurately predict the load. There has to be a perfect power balance in this case. Okay, so that is the reason for all the plants today, the moment grid fails, inverter is shut down. How can it make it work? Of course, if you can make it work, provided you have some sort of a storage. Otherwise, you have to attain the perfect balance between generation and load. And in the absence of the grid, neither you can predict the generation nor you can predict the load. So if there is a mismatch, of course there's going to be a DC voltage will fluctuate. So yes, you can make it work provided you connect a storage. The moment there is a storage, solar may not become economically viable because storage is one of the most expensive, and life of the storage cell, the batteries, lead acid batteries, is just 2 to 3 years. So that is one of the challenges here. Now you see the voltage regulation. Why voltage regulation? Okay, see here are the plants, okay, solar plants, and here the load we are connected to a LV grid. Under nominal load, under normal working, this one there is no solar here. Okay, we all know that because of the line impedance drop, voltage will fall with the load. Okay, when it's lightly loaded, voltage will remain approximately constant, maybe. Now with the PV penetration, what will happen? See, with the PV penetration, see the voltage profile. When there is a nominal load also corresponding to this, voltage profile is improves corresponding to without PV. But then when the system is lightly loaded and there is solar PV, you will see over voltages. Now, how do we address this? So that there is high penetration, high PV insolation, and low load condition over voltage at the end of the feeder. So under voltage can be observed when PVs are concentrated near the substation. Yes. But then since it is distributed, you get to see this over voltage. What is to be done? The voltage mitigation of the static over voltages are See, one way is not nothing new. You all know that reduce the secondary LV transformer voltage by adjusting the trap changer. Allow the PV inverters to absorb the reactive power. We all know that VSI can supply Q. VSI can supply Q. The rating of the inverter is not in kilowatt or megawatt, it is S. VA, volt ampere. That is square root of P square plus Q square. So if the inverter is absorbing Q, for the same P, my S will increase and therefore the cost. So what is being done till the other day? It may be continuing even today. You choose the inverter rating. KVA rating is equal to P. S is equal to P. In other words, you choose the rating of the inverter corresponding to the rating of a nominal rating of the solar farm that you have. If you're trying to increase S to incorporate Q, you have to go in for a higher rating. Of course, higher rating will increase the cost. Okay, that is there, of course. But then it is possible for the inverter to absorb the reactive power. The second way is this is the solution: install auto transform voltage regulator. Most of the power system people would know this, maybe better than me. Increase the conductor size, thereby reducing the impedance. Why is the voltage drop is like this? Because of the impedance, so you try to reduce it, maybe. Or use a surplus storage, you try to store. Again, economically, it does not make sense. Or curtail power from PV unit. Active power curtailment. Active power curtailment. Okay. Now, it may make sense because system is lightly loaded. Otherwise, it's loss of revenue. Okay. So, what are the standard reactive power strategies? One is fixed reactive power, Q. Okay. Fixed reactive power. Each one inverter will supply the fixed reactive power. What is second? Fixed power. Fixed cos theta. Third one is power factor in terms of injected power. Okay. Cause of power. And maybe voltage dependent. We will see in detail. The same plant that I have seen here, reactive power support for voltage regulation. Here are the plants. Okay. All of them generating this. Cos theta is fixed. Cos theta is fixed for all the inverters. So what will happen? As P reduces, see here, as P reduces, Q also will come down. Why? Cos theta is fixed. Cos theta is fixed. So when the system is lightly loaded, or when the solar insolation is low, our generation is low, so automatically Q also will come down. Q also will come down. Now, whether that is a good thing, you have to see what are the disadvantages. See, so what happens at night? In the evenings maybe there is no solar insolation, so P will come down. But then most of the residential loads will start coming into the grid. And these loads are inductive in nature. Grid may require reactive power. An inverter has the capability to supply the reactive power. So unless you program it, it may not be possible. This may not be of much use. The second one is making the reactive power proportional to whatever power factor in terms of injected active power. So the algorithm is see here, as the power increases, algorithm is if the power is higher than this, cos theta will be higher. In between P1 and P2, okay, The cos theta can lie between this area, it's linear. Okay, you can write an equation to that line. And beyond C2, the power. Third one, see here. Make Q, okay, depending upon the voltage profile. Depending upon the voltage profile. So there is some sort of a dead band also. Symmetrical about 1 per unit. So this is leading. So this is a gradual increase, constant Q, gradual increase in the negative direction, and again constant Q. So here is the reactive power that is being supplied by the PV depending upon its location or depending upon the rating. To mitigate the voltage regulation. This is quite popular. See here, the combined reactive power support and active power curtailment for actual method. This is what I said. Curtail the power of PV unit and allow PV inverters to absorb reactive power. What does that mean? See here, assume that the solar insulation does not change. It is remaining constant. Yes, till VLP limit, there is no change. The higher voltage is increasing because of the load condition. So what you do? You curtail the power generation. Okay. And see the reactive power supplied by the inverter. Beyond x-axis is voltage. Okay. So as the voltage increases, thinking is under lightly loaded conditions, solar insulation is high. What is being done is going for reactive power support. Here may be lagging and here may be leading because voltage is low. So gradually increase, remain constant. Okay. The dotted line is for the reduced solar insulation. So the conventional reactive power support method, unnecessary reactive power injection or absorption, ineffective sharing of reactive power, and increased losses. These are the limitations of whatever the technique that I have discussed previously. Okay. But then that's what I said, PVs have limited reactive power capability because S is equal to P plus JQ, okay, and the rating is approximately and then chosen based on the power itself. Now, if I have to choose that it has to supply reactive power also, then my rating increases. So considering highly resistive line characteristics, see here, this is what I told you. The Q required to control an over voltage will be more. Power system people would be able to understand this. Resistive is highly, the distribution network is resistive in nature. So Q required to control an over voltage will be more because generally resistive network, the P is more sensitive to rather than Q. Okay. So centralized regulators will be costly and increases the feeder losses. So intelligent voltage control scheme would be, see here, over voltage scenario, provide reactive power till the rated capacity. If the voltage support is ineffective, curtail the active power because you are supplying the reactive power. See here, you are supplying the reactive power at this point. It has hit the limit. Now what do you do? Yeah, now you curtail the active power so that you can. So the rating, so what has happened is S is equal to P plus JQ. Q has, it has reactive power till the capacity, maybe it's 10% or 20%. That has hit the limit. Now you cannot increase, because if you increase, S is going to increase. That may overload the inverter, and therefore it may get damaged. So instead, what you do? Now curtail P, reduce P. So some capacity is released and use that capacity to supply Q. Okay, this is what it says. Curtailing P increases the Q capability, provide more Q support, faster voltage regulation. So this is what I said. For LV grids, with a Cat6 resistive, sensitivity of voltage towards reactive power is much higher than the active power. Much higher than the reactive power. Because in the transmission grid, what we do is we just supply the reactive power for voltage support. But here, what you have to do is sensitivity to voltage with respect to active power is much higher than the reactive power, especially in the distribution grid. So under voltage scenario, if it is under voltage, provide reactive power till the rated capacity. Do not curtail active power. Do not curtail active power. Curtail P only if injector current losses crosses the rated during. So these are the things you have to do. If under voltage scenario, this is the over voltage scenario. Yeah. If there are any questions, feel free. Island.
Hello, participants. If you have any query, you can ask to sir. Just you raise your hand, we will unmute you. Participants, till the moment, if you have any doubt, any query, you can ask, you can interact to sir, you can, please.
Because continuously I don't want to talk also. I am not.
Yes, sir. Participants, you can raise your hand. Actually, that is the drawback of online sessions.
Online session, yeah. Now time you start conducting offline classes.
Yes, sir.
Because I don't even know whether the participants are understanding or not. मैं कुछ बोलते जा रहा हूँ, समझता नहीं. मुझे पता नहीं है participant को समझ में आ रहा है कि नहीं.
Any participant? If you have any query, you can ask. Yeah, someone has raised the hand.
Yadav, yeah, Gaurav Yadav.
Yes. Let me allow his mic. Yeah, now you can unmute, Mr. Gaurav.
Hello, sir. So my name is Gaurav Yadav and I'm from DTU, PhD scholar. So I want to ask that you were telling about standard reactive power strategies. So, sir, in that you told about the power factor in terms of injected active power. So can you, sir, please elaborate that point for me?
Do that again.
So that point, that power factor in terms of injected active power.
See here, what is being done? Cos theta is fixed. Okay. Now, so if the solar insolation remains constant, P remains constant, and therefore Q also remains constant. Now, solar insolation is reducing. So therefore, what will happen? P will come down. Power factor has to remain constant. That is the strategy. So what will happen? Q also will come down automatically.
Okay.
You got what I'm saying?
Yes, sir.
So what is being done here? So what is the relationship beyond in this region, P1? Okay.
Yes,
Cos
sir.
theta is constant. Between P1 and P2, yeah, it is given by this expression, this straight line. And beyond P2, it is C2.
Yes, sir.
So here I said, in the sense, if the P is 0, P tends to 0, Q also will tend to 0.
Yes, sir.
So I do not know whether it is good or bad. Just see now. That's what I said in the evenings. In the evenings now, yes, solar insolation is reducing, power generation is low, so inverter is almost maybe shutting down. Shutting down. Instead, you have Q based on the voltage profile. The voltage.
So voice is somewhat lagging.
Huh?
Voice was
Hello.
somewhat interrupted in between.
Instead, this is the most I think accepted norm, or this is what is combined reactive power support with active power curtailment. Depending upon where you are connected your inverter, is it LV grid or HV grid? I'm talking about rooftop. In the rooftop, that therefore definitely is LV grid, but the LV grid is fairly resistive. Now, yes, it is not the same thing as the Q support in an HV grid. HV grid is fairly inductive, isn't it?
Yes, sir.
So this is what it is. So you may have to curtail the active power. So here the conventional. So this is what is being done. Intelligent voltage support schemes for over voltage scenario and under voltage scenario.
Okay, sir.
Anyone else?
And here you see what happens. Solar generation. Here there is a load here. The excess only will go to the grid. Am I right?
Yes, sir.
Now what will happen in the sense, say lightly loaded condition when the solar installation is coming down, all the PV load, that PV power that was generated may be consumed by this load itself. So at that time, what will happen to Q? So we will not supply any power to the grid, but all the power that is generated will be consumed by the load itself. So these are the limitations we have to address. So this could be one such method.
Anyone else? Any participant can interact directly to sir. Just you raise your hand, we will unmute you.
Yeah. Okay. Let us go ahead. Islanding detection. Yeah. The portion of an area electric network is still energized under grid failure. Yeah, these are the various things, intentional, unintentional. Now we are talking about intentional, we can always do, that is not the problem. Unintentional is the problem. Unintentional islanding, how do we detect? And what all control methods? Yeah, look, there are various techniques in local techniques and remote techniques. Okay. Remote techniques are maybe from the substation. You can do it by communication method. Now there is a I don't know how reliable it is now because of the sophisticated networks. It may be possible to realize this, but then we'll talk about not about the remote techniques. Now, here is a conventional system. Just listen to me carefully. Initially, the inverter was supplying power to the grid. This was closed, breaker was closed, it is feeding, and there is some steady state was attained. Okay. Now, what happens if when I open or when the grid has failed? There are two possibilities. And generation will still remain the same. There is no change in the generation. Okay. So this was the inverter was supplying P plus JDQ. P plus Q, it was supplying some P and some Q was going to the grid, and some P and Q was going to the load. Now, when the grid is open, PG plus JQ has become 0. Okay. How do I detect? Which quantity should I see and predict that grid has failed? NDZ stands for over voltage, under voltage, over frequency, upper frequency and lower frequency. Okay, so the limits. So this area should be as small as possible. The area should ideally we should have something like this, but it may not be possible. There has to be a change in the voltage and there has to be a change in the frequency. Only then our control system may be able to predict or will be able to predict, yeah, there is an islanding system. Now, under what condition frequency will change, under what condition voltage will change. What is happening in the conventional system? Grid has failed here. Okay. Now, what will happen to the generator? We know that the moment initially it was supplying power, grid has failed. Mechanical input has still remained the same, and therefore generator starts speeding up, frequency will increase. Okay. What will happen in inverter fed or solar PV inverter fed grids? If there is a mismatch of power, see here initially, now you have to consider case by case. Okay, we'll assume that there is a mismatch of power. Okay. Initially, the power that was going to the grid, now it has become zero. It will try to flow in the local load. Assume, of course, local load I have a resist. There could be RLC type of a load. You can model it in that way. This active power has to be consumed by a resistive element. So that in-phase component will flow through the so-called equivalent resistance. And therefore, voltage will change. Remember, voltage will change and not the frequency. This is the difference between the generator connected to the grid failing. In the generator connected to the grid failing, if there is a mismatch of active power, frequency will change. Whereas here, inverter fed, solar PV inverter fed, PV inverter connected to the grid, if there is a mismatch of active power, when the grid has failed, voltage will change, not the frequency. So what will happen when the reactive power change mismatch? Now this reactive power has to flow through, should be consumed by this L and C. Okay, it cannot be consumed by this resistor. So initially there was a steady state. Okay, some QL was going. Now initially you're supplying more Q. So definitely now the frequencies will adjust such that they will start. Oh yes, steady state is attained, because some of this reactive power should be supplied by, that should be QL. Reactive power supplied by the capacitor and the load, that should match QL. Now the more Q is coming, okay, because there's a mismatch. So what will happen? The frequency of the system will change to accommodate this change. So remember two things. One is, if there is an active power mismatch, magnitude of the voltage, terminal voltage will change. And if there is a mismatch of reactive power, frequency will change. Unlike in the conventional generator connected to the grid. Okay. This is the communication based network that I was talking about. Communication network, they will see Whether breaker is opened, the substation person will send it a signal to the inverter or communication to the operator to shut down this inverter. Okay. Here, the impedance network that is connected here, okay, capacitor, they will check in the sense if the breaker is open and if there is capacitor, depending upon the position, my Q will change, and therefore the frequency will change, and therefore they can detect. So these are the impedance insertion. So time and sometime, depending upon the time interval, they will connect the capacitor to the grid, okay, and they will change. If the grid has failed, they'll check whether the frequency, there's a change in frequency, and they'll take an appropriate action. So you see here the simulation results. We have done this with active power mismatch. Okay, power supply voltage. This is the grid voltage. Okay, grid current, blue, and this purple could be load current. And at this point, the grid has failed. At this point, grid has failed. The blue line has become zero. Current is becoming zero. See here what happens to the frequency. It was 50. You're trying to change. This 50. This is 50.5. Frequency tries to change, but then finally it will attain a steady value, 50 hertz. Momentarily there is a change. But what happens to the voltage? You see, there is an increase in the voltage, increase in the terminal voltage. This is prior to islanding. Yes, when it is islanding. Reactive power mismatch. Okay. See, at this point, grid current becoming zero. Okay. Let's see here. They are not perfectly synchronized. Around about 0.41. Grid has failed. Now frequency 52, it comes to around 48 or so. No change in the voltage. No change in the voltage. Unlike here, frequency momentarily there is increase to a very low value, but then it will attain the same old value. Whereas, and here, the voltage add to this. Third case, the generator was actually here, the inverter was floating in the bus. It was floating, neither it was supplying P plus PG plus JQG, both are zero. Both are zero. In other words, this inverter was just floating in the bus. That's what we say. Whatever the power that was consumed, whatever the power that was generated was being consumed by the local load itself. Okay. Now the grid failing. Grid has failed. See, there was no current was flowing. No current was flowing. See here, another thing I did not observe was here the current was unity power factor current. Unity power factor current. That's how it is. I said active power mismatch. Active power mismatch. Okay. Whereas second case is lagging current. Lagging current. Lagging current. Yeah. So reactive power mismatch. Here, current fed to the grid itself is zero. There is neither active nor it's fed. So either there is a change in the voltage or there is a change in the frequency. 4-1. How do you detect this? This one you may be able to detect. But then, if the change in frequency is so low or change in voltage is so low, if it is within this NDZ, okay, zone, your inverter will not trip. Follow what I'm saying? Under voltage, over voltage. Over frequency limit, under frequency limit. In the sense, when there is frequency change, when there is a reactive power change, frequency will change. So for operation, the inverter will be tripped or controller will trip only when operating point falls outside this area. Now, if the change in voltage is so low, and if it does not come out, this one, your circuit will not trip. Or inverter, your control system will not act. How do you make this the so-called grid, so-called the NDZ area tending to zero? This, even if it is tending to zero, and here there was no active and reactive power mismatch. Grid has failed, a inverter has to trip. How will you incorporate it? See, there are various techniques. See, here it shows just a plot of drift the frequency. In active islanding techniques, I have to push the frequencies to say 2 hertz or so. It depends on the Q of the load. See, from 50, assume that you are working at our frequency is 50, you can go to 51 or 49. Okay. Now see the amount of Q that is required to change the frequency by 1 hertz. And the Q factor of the load, Q of the load is 1, you may require around 7%. So you require 7% reactive Q to change the frequency by 1 hertz. And if the Q factor of the load is 2, you require around 16% or so. 16% or so. This could be around 8 and this could be around 16% Q. It is very high. It cannot be possible to have that much of capacity. Okay. To drift the frequency by 1 hertz. 1 hertz. So what should be, is there a way to do this? Yes, there are ways. One is positive feedback frequency shift, ID technique. Positive feedback frequency shift. When does the positive frequency shift happen? Active power mismatch. Active power mismatch. Only then the frequency, I'm sorry. The frequency, positive feedback frequency shift, that will happen when there's a reactive power mismatch. When there's a reactive power mismatch, there's a frequency shift. When the active power mismatch, there is voltage shift. Okay. Now you'll see positive feedback frequency shift. What happens here? This is a control loop. Okay. What is being done here? See, inverter supplying power to the grid. Okay. Every grid connected inverter has a phase lock loop. Okay, PLL. Okay. You will sense the load. From the PLL, you will get a frequency. Okay. Load current is being sensed. This current is being sensed. I have theta. I can convert into ID and IQ component. Now what I will do is, see, here there is omega, and I'm assuming that there is a small change in omega because of islanding section. Now this delta omega, depending upon the magnitude delta omega, I'll convert it to equivalent current, and I will add it to some reference, IQ reference, the quadrature component. Okay. Now, what will happen? This is the actual IQ. This is the reference processed by the PI controller. Okay. This is the new. So these two components are converted to alpha beta, the PWM converter, and will go. Under normal circumstances, there is no change in the frequency, this will be 0. Under normal condition, this will be 0. Why? There is no change in frequency. Okay. Now, if there is a grid failure, definitely omega will be some finite value. Okay. So what will happen? I'll sense omega, and therefore IQ reference will change. This IQ reference will change. Why? IQ reference is now plus delta I. This reference will go. Now IQ reference is changing now. Therefore, Q will change. So if Q changes, omega further deviates. Omega further deviates. So it will go out of phase. Somewhere here, see the result that I'm showing. Technique. Later, yeah. Now, second one is positive feedback voltage shift based ID technique. Here, the quadrature axis component was shifted. Here, the d-axis component will be shifted. That's it. Nothing is there is no change at all. But then here you have to do to the voltage. I will sense the voltage now. I will sense the voltage for the active power mismatch. Okay. Oh yes. If there is a small change in the voltage, that will reflect it at delta V. And that will be added to ID reference. ID reference. Now ID references will go on changing it, and therefore it will change the voltage. See here, we sense there is a change in small delta V, so ID reference will increase. Okay, ID reference will change. Will be P reference will change. Now if the P changes, again voltage at the PPCC will also change. So there is a positive feedback, and it will go away from the operating point, and therefore now what is a hybrid technique? Combination of both. Combination of what is being done is, see here, only this side. A small low frequency oscillation is given here. The low frequency oscillation. See, this is the omega term will come, change a small change omega. Okay. See, this will act when no change in for this case, no reactive power active power mismatch. So what will happen here? Omega does not change, okay? But then you are purposely changing the reference by giving a small disturbance. Under normal operation, this will not affect when it's in a grid connected system. Grid connected system, there is a small oscillation in Q. It will not affect the frequency. It may not even change the okay, because grid connected frequency is tightly held constant there. When the grid has failed, this small change in the frequency will affect your omega, maybe very small quantity, delta omega. Now that will be again here added. So it will go on. IQ reference will change. So these are all, of course, omega LD and omega LQ. It comes in a synchronous rotating reference frame. You have to add these terms, and you can detect it. See here, the simulation results. The effect of RPV on frequency islanding, regulating the reactive power. So what is being done? See, I'm just changing the Q. Frequency also changes. But then adding the positive feedback PFS system here, PFFS, that is active power. Okay. This loop also has to be done here. Both we are combining. Now what will happen here? See here. Same change. Frequency goes and hits the limit. Okay. Q around 4% or so. and delta PQ is just 4%, 0.04. Will remain constant. Frequency has gone 50 Hz. Just continuously oscillate, it may not trip. So decreases the reactive power reference in normal mode of operation. So no NDZ here. NDZ. Here you require the percentage of reactive power to create an oscillation is pretty high here, but then this has now islanding detection for grids with multiple PVs is a challenge. We could do here for one inverter all this oscillation. We have multiple inverters. Now, what may happen? Or what we should do, what we ensure, this disturbance should be, whatever disturbance that you're creating, it should be synchronized with other inverters. So this is what it says. Passive mode methods NTZ, active method created disturbance affects the power quality. One, and see, PVs are operated UPF, synchronization of variations are not guaranteed owing to averaging effect fail to detect an island. Because what it means is the disturbance that you are given to all the inverters cannot be able to synchronize them. So one giving positive, another one is getting negative. So because of the averaging effect, it may not be possible for you to detect. So something different techniques have to be found out if you are going in for multiple PVs. Multiple. Now, why low voltage right through LVRT? Each inverter should have LVRT as well as HVRT, high voltage right through. This short duration voltage disturbance disconnect. PV should not be disconnected from PV. Should not be short duration. Large number of PV systems disconnected. What will happen? What may happen? The percentage penetration is very high. Okay, and if there for a small disturbance, if the PVs are getting disturbed, PVs are getting disconnected. Okay, and the grid connected. If there is a large number of such inverters getting disconnected, there could be blackouts because a lot of generation and 30% generation has gone because we are 30% penetration. Because of small disturbance, 30% generation is gone. There could be that will affect the grid. The 30% power goes means definitely load on the existing generators that's come. The frequency will drop there and it may trip. But then this is not acceptable. So stay connected to the utility grid. So you require a right-through operation. Right-through operation. So you should distinguish an islanding event. Distinguish the islanding event, a short disturbance required for right-through operation and avoid consequence. You should stay alive. If you see, that's the reason. If you see here, voltage has become zero for some time. Okay, so this is various standards for Belgium, Spain, Germany, and Taiwan. So if you are selling the inverters in the international market, it has to satisfy this condition. For Germany, 100% voltage, it comes to zero. There's a short circuit for a very short duration. Short circuit recovers voltage to 30%. And in this area, your inverter should not trip. Should not trip. So this is for Germany, for depending upon the country. So for all these disturbances, inverter should stay connected with the system. So here is the LVRT curve determines the voltage levels and time duration connection for the. So these are the limit, normal working range, 1.1 per unit to 0.88 per unit, normal working range. Okay, and this is for, see, even the voltage becoming low for TOO2. This time zero voltage period is around 0.16 seconds. Just see that's equal to how many cycles? Maybe it looks like it is more than 10 cycles. So you have to stay connected and see the voltage UV2. UV2 is 0.5 per unit. So voltage falls to zero short circuit for 0.1 seconds, recovers for 0.5 per unit. For how long? TUV2. TUV2 is up to 2 seconds. Up to 2 seconds, this voltage is 0.5 per unit. Again, it recovers to UV1. UV1 is 88.88. Okay. And continues to remain one. You have to stay connected. So in this entire region, you have to stay connected. Same is the case for over voltages also. See here, over voltage OV2 is 1.1 to 1.2 per unit. This is 1.2 per unit. This is 1.1 per unit. In this area also, you have to stay connected. Why over voltage is a problem? Over voltage is a problem means now you have to devise how to block, or whenever you switch, the voltage will change from 1.2 per unit to 0. The switching losses will increase. Now the inverter also, in addition, device also have to block a higher voltage. So you may not have chosen the devices accordingly. So that's the reason. Now entire redesigning of the inverter, or you have to redesign the inverter, has to be done. So LVRT code determines extended clearing time to abnormal voltages are mentioned in amendment 80, and these are becoming stringent day by day. This is already over, I think. Now, conventional LVRT schemes are this. The majority of the grid code insist on what is happening here. This is they connected. It's a dead band. It's a dead band also. Okay. So this is a LVRT range, and this is a HVRT range. Okay. So for LVRT grid, level express injection of only reactive power is not an effective way of voltage support. I told you that, for a low voltage grid, a low X/R ratio, injection of reactive power is not a solution. You have to either, depending upon over voltage, under voltage, you have to do certain P sometimes. Flexible active or reactive injection is a better technology. Now, what will happen if the grid is unbalanced? What you do? Sometimes unbalanced grid during LVRT. The active and reactive power injection in both sequence frames, so as to provide better positive sequence voltage recovery and negative sequence voltage reduction. Whatever that you do, what you should ensure is positive sequence voltage recovers and negative sequence voltage reduces. This you should do while ensuring or during the unbalanced voltage grid condition. So here are some of the simulation conditions: LG fault, okay, LL fault, and LG fault. So your voltages are unbalanced now. This is the voltage and currents, grid current and voltages are unbalanced. So what should a controller do? What a controller should do in such a way that positive sequence voltage recovers and negative sequence voltage diminishes. What is to be done? And what should you do for the converter at this point? See here, suppose the grid has failed. Now grid has failed. Solar power is coming continuously. Okay, there is no load to absorb. What will happen? That power has to be absorbed by this capacitor. So if the capacitor goes on absorbing, the voltage will increase. Voltage will increase. Definitely this inverter will fail. So what you should do? Maybe all this time you may be operating at MPP, maximum power point. That is what is being done. So the moment the grid has failed, yes, you have to come out of MPP. Your power generation has to be reduced. The proper power balancing between MPP operation converter required. harmonic compensation, LV grid, increased losses, non-Indian losses, harmonic currents. I'm not going to talk. These are the THD limits. How will you mitigate it? How will you mitigate it? Okay. This is being done by assume that fortunately we have a voltage source. It can generate. It can, of course, if the load is everything is fine, it can generate a sinusoidal current, or it can generate any harmonics. So that can be done by suitably switching the converter. So what you do first, you have to calculate the harmonics. You have to determine the harmonics, and those harmonics, if the inverter generates. So now grid need not supply those harmonics. What you need to ensure is, yes, you have various loads. So harmonics, if the inverter is not supplying, grid has to supply. Okay. So grid codes will not allow for you to connect this load. So therefore, these harmonics have to come from this VSI, and VSI can generate these harmonics, okay, by suitably switching it. That is not a problem. There are various techniques. I think there are a lot of topics to be done based on single and three-phase inverter. I will stop here. If there are any questions, maybe the remaining topic, maybe we can discuss sometime later.
Thank you very much, sir. Thank you for wonderful delivery of the contents. Now I would like to invite participants. If you have any query, you can ask to sir. Please raise your hand. We will unmute. Otherwise, you can write your questions in the chat box, and you can directly ask to sir from the chat box.
That is fine.
Some
Gaurav Yadav again, yeah.
Just a minute. Gaurav, you can ask. Hello, Gaurav. Your mic is enabled now. You can ask, please. Mr. Gaurav. There may be some problem from his side. Anyway, sir, you have covered a lot of things, and I hope so participants enjoyed the session. And basically, this was a wonderful session for me also. I have learned a lot of things from this session, sir. And now I would like to invite our respected principal, Dr. Joshi, sir, to give some farewell comments.
So, not taking much time, I thanks Professor B.G. Fernandez for delivering such a useful content. As his peculiarity, he has delivered the concepts of operation of the converters and so on, which are not easily understood when you read any book. So that is his specialty, that he addressed the core concepts almost in every lecture. So sir, thanks for that. And thank you for sparing your valuable time. I know you are extremely busy, but then again, you have given respect to us by accepting the invitation. Sir, thank you very much.
Thank you. Namaskar. Thank you so much.
Thank you very much, sir. Thank you.
If there are any questions, they can send me an email. If there are any questions, I will try.
Yes.
you can share my
Participants, you can directly send your question to Fernandez sir email. The mail is available on the website of IIT Bombay. You can directly access it. Right. And thanks once again, Dr. Joshi sir, for continuously connecting for these 2 hours due to your busy schedule also. And we are very much thankful on behalf of Government Engineering College Bharuch and organizing team. We are very much thankful to Fernandez sir. Sir has always accepted our invitation. This is the third lecture within a year. Thank you very much, sir. Thank you. Thank you very much, sir. Thank you. Now, participants, this is the now lunch break time. We will meet once again at 1:30 sharp. Please, you have a nice lunch, and then we will meet again.
Giri sir.
Yes, sir.
I really want to appeal to the participant that they should be make the sessions interactive as possible. See, BJF sir is delivering is very good content which is useful for many researchers, and the faculty members who are participants are not interacting. That is not a good situation. Faculty should listen and then raise the appropriate questions. This should be attentive. That is very well required.
Yes, sir.
So I don't know.
Participants, yes, sir. Please continue.
Even my delivery also very few questions. One question only. Even SN Singh sir's lecture, there was only one question. Even BGF sir's, no question. Only one in between. Oh, that is not a good situation. We have put our efforts to bring best experts across the India. See, that is not achieved freely. We have used our personal contacts to deliver best to the faculty members, right? And now there is a responsibility on the shoulders of faculty to make this FDP more successful by giving more attention and make all sessions interactive. So this is something which I don't like. Faculty members should think over it.
Thank you very much, sir. And I think so they are listening you directly, and still 3 to 4 sessions to go. And I hope so you all are paying attention to the words of Dr. Joshi sir. He is personally taking very much interest for making this FDP successful. That's why it is our collective responsibility to attend the session very carefully, make the sessions interactive. I am continuously appealing about your attendance also. Dr. Joshi sir, being a senior principal of this institute, he is continuously appealing. So you all are requested to pay attention on his words, and please attend the sessions with full interaction and with full zeal and energy. Thank you, Dr. Joshi sir. Thank you very much for your valuable words and suggestion. I hope so participants will paying enough attention to your words. Thank you very much, sir. Participants, now we will meet again at 1:30. Now you take the lunch, and we will make our sessions. I will start my session at 1:30. And in my session today, I will have some coverage of live simulations as well. So you will enjoy the session. I hope so. You please come in maximum. Thank you very much. component, right? Because active power must be that means the active power, total active power in the system. What is the total active power in the system? That means active power demanded by the load and losses occurring over the inverter. That's why a loss component is coming from the DC bus voltage imbalance, and that is added over here, taken 1/3 for making it voltage balancing, and it is WP, that means it is going to feed back, right? Because this is the convergence relation. For updating one weight, you need the previous step weight. That's why you have to take feedback. Whatever you are getting here, you have to make it feedback for this control algorithm. And again, entire calculation will go on. It will be continuing unless and until error is not going to be 0. So this is the process, entire process of how Adaline control is working for estimation of the reference current. And once reference current is estimated, we are comparing from the actual source current, and finally modulating signal will be generated for the PWM controller, right? And the previous steps are same, only thing is we are not using any PLL in this control, right? Just we are estimating the voltages. Templates are nothing but, suppose UPA, UPB, UPC. What is UPA? You know, supply V equals to Vm sin omega t. It will be divided by Vm once again. Then it becomes UPA becomes sin omega t. Similarly, it becomes sin omega t plus 120, and it becomes sin omega t minus 120 and sin omega t plus 120. So these three phases will be calculated directly, and Vm you can calculate by under root 2/3 VSA square plus VSV square plus VSC square. Things are given in the literature, and they can be converted into quadrature as well by one matrix. There is one matrix, and in phase, these are known as in phase. In phase means where voltage and current are in the same phase, right? In phase components, and then because in the reactive weight calculations, quadrature components are required. That's why conversion is required. In phase to quadrature phase conversion is required. And there are two controllers, outer control loop where DC reference is set. As I told you in the previous my session, what should be the DC reference? If we are working at 220 volt PCC voltage, our DC reference must be near to 400 volt, right? And actual DC is sensed from there, error is calculated, it is processed through PI controller, and ultimately this loss component will be generated from the PI controller, and that will be added along with the active components. Similarly here, from the VA-BBVC, we are calculating the terminal voltage. The relation I told, under root 2/3 VSA square plus VSB square plus VSC square, and finally reference voltage is set over here, and actual voltage is estimated or calculated. Finally voltage error will come, that is processed through the simple PI controller. And we are getting here the some reactive current component, and all reactive current components are added, and it is subtracted from the PI controller loop, so that the difference must be supplied from the generator side, right? And finally you are getting the reference, and through comparison we are getting the pulses for the converter. Now another control, what we can say, that is the class of intelligent controllers, back propagation feed forward network controller. Basically the philosophy is here, BPFF based control regulates the voltage and frequency of the microgrid or distribution generation. In this scheme, multi-layered feed forward network consists of input layer, hidden layer, and output layer. There are three layers in any neural network: input layer, hidden layer, and output layer. And the concept of the neural network is same as this one. This is the basic neural philosophy in terms of Adaline. This is known as Adaline, the full form of Adaline. Anybody knows? Anybody knows the full form of Adaline? Adaline is short form of anything. What is the full form of Adaline? Anyone? Are you listening me?
Yes, sir. Adaptive linear in neuron or later adaptive linear element.
Other participants? I think so. They are not. This time we have got. Okay, anyway, they are not listening. And the input signal passes in feed forward direction from the input layer towards the output layer. What I am discussing here, that is very important for the people who are working with some neural network topology, control algorithms, or they are working align, or they are working some adaptive control algorithm. Fundamental philosophy is almost same, right? So the input signal passes in feed forward direction from input layer towards the output layer. Ultimately, whenever signal is traveling from input layer towards output layer, what will be the concept? Multiplication from the input signal to the synoptic weight, then aggregation, then activation function. Hello? You raised the hand, okay. Okay, just. Okay. Yes, now you can ask, please. Someone has called me. Yes. Now you can unmute yourself.
Yes, sir. Am I audible, sir?
Yeah, now you are audible, please. Go ahead.
Yes, sir. Actually, that time you asked about Adeline, sir. I am trying to say answer, but I am unable to unmute. Please allow me like this, sir. Whenever I will have a doubt, so that I can unmute myself. That is the reason.
Okay. Thank you.
Thank you, sir.
Yes. Now, if you have any doubt, you can raise your hand, or you can just directly unmute yourself and ask the question. Otherwise, what can I do? One thing, I should allow all. Let me allow everyone. Who is here from the organization? Professor Shah, sir? PK Shah? Okay, anyway, if you have any doubt, you can ask this. Somir, please inform if someone is raising hand, okay?
Yes, sir.
Okay.
Sir.
Now, in this, what we were discussing in the back propagation feed forward network controller, there are three things actually: input signal multiplied by the synoptic weight, and then aggregation of all the layers. You are getting one output, right? And by applying the activation function, again you are multiplying activation function with the input of that function, and finally you are getting the output. So this is one layer philosophy, right? Suppose there are three layers in the neural network. What will you do? You will take the input signal, multiply the synoptic weight of the first layer, aggregate all, then finally go the activation function multiplication, and then that becomes the input for the second layer. So this is the philosophy we are applying here, and input signal passes in feed forward direction from the input layer towards the output layer on layer by layer basis, right? That's why I was telling it. The supervised learning with backpropagation algorithm, supervised learning, that was the third equation what we have taken in the neural Adeline network. In Adeline there were three things: filtering, error detection, and then finally convergence philosophy. So that convergence is nothing but supervised learning, right? Because we are defining there one learning rate. Generally, the value of learning rate is in between from 0 to 1. Generally, in suppose if you are working with solar or wind, you can take it 0.7, 0.6, 0.8, and you can get the desired result. Right. Now you can see the mathematics, what we are doing here. This is the initial weight and this is the input multiplied by the load current, ILA, UPA plus ILB, UPC. This is nothing but we are doing the aggregation, right? And we are getting the ILPA. By applying this activation function, ultimately you are applying the activation function. Sigmoid functions are generally used in the neural network, and this will be multiplied by this ILPA. You will get another value. You can see here IPAL equals to omega 1 plus omega PA x PA plus omega PB x PB plus omega PC x PC. Similarly, this is the active weight estimation or active part of the load current estimation. This is the reactive part of the load current estimation. And these are some constant values. These are the synoptic weights you can change between 0 and 1, right? Sometimes we are, that means some initialization is required, right? And these weights then finally through this relation, this is the same relation actually, omega PA equals to omega PT plus eta. Eta means nothing but learning rate, and then this is the error of the previous one, right? And then this is the input, that is UPA. Here it is written as X. So this is the active weight estimation, or you can say active weight convergence, and this is the reactive weight convergence. And finally, PAL is taken as sigmoid function is used here, and PAL is calculated upon 1 plus e raised minus I PAL. This is already you have calculated, and then similarly QAL will be calculated by using this function. And finally, once all are calculated phase wise, we will take the total of this averaging. So PAL, PBL, PCL by 3. This is done for the load balancing act, so that per phase whatever the weights are reflecting, per phase currents should be same, right? There should not be any kind of unbalance. That's why we are averaging over here active as well as reactive. So these things can be seen here from the block diagram. This is the back propagation network equations. Here it can be used for this one for this block. It is used like ILBQ and IPBL, right? And this equation, the same equation what I was telling, is used for the calculation of PBL and QBL. Similarly, for phase A, phase B and phase C, they are used here. And they are, that means all the actives are summated over here, all the reactives are taken addition over here and divided by 1 by 3 using some very low pass, that means cutoff frequency low pass filter. And finally we are getting the we are getting the active and reactive weights. We are getting here active and reactive weights multiplied by the templates. We are getting, just you multiply these WPS by these templates, in phase templates. QS will be multiplied by the quadrature phase templates, and finally we will get the reference for ABC, and right, other things remains same. So by this way we can understand how the back propagation control algorithm is functioning. This is another control based on momentum least mean square adaptive control algorithm for the power quality in DG. Basically, what is the difference between the basic Adaline and this additional term? Actually, in Adaline we have seen only these two terms, but the third term, that is the momentum term, is used to accelerate the convergence process, right? This acceleration factor is involved here, epsilon. If you see carefully, it is epsilon. The value of epsilon, again, it is fixed value, but suppose convergence process is slower, you can change the value externally and you can feed into the network, right? That is, this is the learning rate and this is the acceleration factor. That means learning rate is always involved, whether you are using back propagation, whether you are using Adaline, whether you are using MLMS, because that is the basic philosophy to train the network. How to train the network. Supervised learning control always requires some learning rate, right? And here acceleration factor is the additional term. And again, entire thing is arranged in 3 blocks, because in each and every block, active reactive calculation is given. Suppose this is for phase A.
Sir.
Yes.
Sir, can you please make it full screen? The bottom part is not coming. I think the tab is coming. Please make it full screen.
Just a minute.
Thank you, sir.
I think so. This is full screen, not full screen. Okay, you are right. Now is it coming?
Still that.
Actually, this
tab is coming.
this bar is coming, and that is one
Otherwise,
limitation.
you can. I think if there is any possibility, you make it shrink, sir. I think it won't come.
We can do one thing. Just a minute. I think so. We are dealing this slide, 44th slide. Yes. Now is it coming?
Yes, sir. It is fine, sir.
Okay. Now you see. Yes, thank you. Basically, what is the difference between the Adaline theory and momentum least mean square theory? And both are working on the same principle, but only minute difference. Actually, I have worked on this theory, and this theory is published in IEEE Transactions on Industrial Electronics. And reviewer has asked me one question: what is the basic difference between this and the previous Adaline? Then I suggested, I given this answer. This is the additional term, and we have shown in the results as well what is the difference what we are getting by adding the third term in the basic Adaline network. Basically, this is based on you can see it is somewhat, if we know the NR method of the power system, Newton-Raphson method, we are using something plus added with error. So this is the weight, previous weight ZK minus 1 and the updated weight, and this is the difference of the that means difference of the weight from one step to another step and multiplied by the convergence factor, or you can say acceleration factor. So ultimately we are getting faster convergence, and we have proven in our results just by comparing from the basic Adaline and the results. People were convinced, yes, actually this is faster due to presence of this terminology, this term. So other things are same. We are calculating the active components of phase A, active component of phase B, reactive component of phase ABC, and finally they are adding and averaging, and we are getting one average value of the weight, and finally that weight is fed back, just basic Adaline. Weight is again going back, here also weight is going back, and they are used in the convergence process. And finally we have used here because I was using the one induction generator, that's why frequency is sensed instead of DC link. Frequency, reference frequency is 50 Hertz. Actual frequency we have estimated through calculation, not through PLL. PLL actually it is not reliable in the faster dynamical conditions. That's why you have to estimate frequency through mathematical blocks, and these frequencies estimated with the help of comparison, actual and reference, they are compared, and error is processed through simple PI controller, and then again we are getting the loss component, it is added with the overall active component of this, and finally we are getting the active component for the source reference, right? Reactive component similarly, this is the root. And what I was talking about the equations, you can see here the equations are given. 0.66 means it is nothing but 2 by 3 VSA square, VSB square, VSC square, and these are the things you can see the calculation of weights calculation of you can say in phase templates, VSA divided by this. This is the magnitude at PCC actually, and this is the supply voltage Vm sin omega t divided by Vm. It becomes sin omega t minus 120 and sin omega t plus 120. Basically, there are three weights calculated: PA, PB, and PC. And quadrature phase template calculation is done here. You will get quadrature components over here. Basically, X PABC is used here, and this is multiplied by this active weight. This is multiplied by active weight, and this is multiplied by the quadrature weight. Finally, we are getting three components of reference phase ABC here, active components, reference of phase ABC in the reactive domain, and they are added to each other, and we are getting reference for phase A, B, and C. Actual current is sensed through sensor components, and ISA, ISB, ISC, they are compared and given to the PWM controllers, and finally we are getting the pulses for the converter. So this is another intelligent control, and these weights, the intelligence means what? Where intelligence is involved? Intelligence is involved in the automatic update of the weights. These weights will be automatically changing to make the error zero, right? So this is the basic philosophy of the intelligent control algorithm. Now, again, this is one radial basis function control algorithm. It is again similarly the same thing what we are doing in the this one, first one. The same equations are utilized over here, right? Whatever you have seen in this back propagation. The only thing is just you see ILP calculation is there, and finally you are calculating WP with the help of ILA, ILB, ILC. All these are calculated. Sigmoid function is again used, and normalization. Normalization means 1/3 we are using, taking averaging, and finally we are getting it here and then feeding back. The concept is same. Once you are well acquainted with any basic fundamental control algorithm, there will not be a problem for understanding in the another control algorithm. All these philosophies are same. There is no change at all. And these are some simulation results when we were simulating the system by using wind speed, fixed wind speed, and variable load. Wind speed means our system is DG and generator is running with the wind prime mover, right? And load is connected. Some kind of where I shown in the block diagrams. Yes, this kind of system basically. Yes, this kind of system where generator is supplying to this load and compensator is used here. This is isolated system, but we can say this kind of system where this is 3-phase 4-wire load. Generator is run by the turbine. So this is the basically system where we are applying the control algorithm to fire the switches S1, S2, S3, S4, S5, and S6. That's why always we are generating 6 signals from each and every case. And what is our objective? Our objective is to supply fundamental current from the generator. Our objective is to supply or maintain balanced current at the generator terminal despite the unbalance over here, right? So all these and harmonics separation should be taken care by the compensator. There should not be any harmonics at this end. So this is the system where we are applying all the controls. You must know where we are implementing the control algorithm. So this is the system where we are implementing all the control algorithm. You can change some philosophy in the system. You can change some topology in the system, but more or less system is same. Now, how to analyze the results? Which kind of results you are expecting? So we can see here with the fixed in wind speed and variable load, we have run the system and we have implemented the control algorithm, and we can see here when we have introduced the transient at 7.5. At this moment we have introduced the transient from the loading, because you can see this is the non-linear load. All the phases are coming over here, but after this point there are only 2 phases. That means we have made unbalance from the load side, but either that unbalance is reflected towards the generator side or not. So we can see here the supply current, it is almost balanced. Okay, due to reduction of load, somewhat current magnitude is decreasing, but there is balance in the system. Similarly, there is no change in the envelope of the generator voltage. So basically, and this is the compensator current, and other parameters like terminal voltage remains same near to 190 battery voltage, because we are using the battery in the system, standalone system is running, that's why battery voltage is kept fixed. And then frequency is another parameter. You can see here, when you are decreasing the load, frequency is somewhat going up. That means because generator will feel less load and it will try to accelerate, but due to controller action it is accelerating this from this moment to this moment, but after this again it is we can say stabilized. That means you are getting the near to 50 hertz only. It is taking almost, you can see here, 7.5 and 7.52. After 7.52, frequency is controlled. That means only 0.02 second, 0.02 second. That means how much is the time per cycle? That means we can say here 0.02 second, 0.02 second multiplied by 1000. It becomes 20 millisecond, right? So 20 millisecond means nothing but, I think so, 1 cycle, right? Within 1 cycle, controller is controlling the generator, right? That means there is no disturbance. 20 millisecond time is not very much time for any inertial system, because generator is inertial in nature. It is having certain inertia, and 20 millisecond, if you are controlling anything like frequency and voltage, it is good enough, right? Similarly, we can see the change in the battery current at this from this transient. If you are introducing the transient at 7.5, battery current starts you can say fluctuating. Now it depends on the loading condition. Whether load is more than the supply, battery will be going into discharging mode. When load is less than the supply, battery will be going into the charging mode. And these are the neutral currents. Actually, basically zero sequence current is always having we can say 3 times frequency from the normal frequency. Suppose if zero sequence current is present, then it is basically 3 times 3 omega n frequency is there. That is the one, we can say, that is one identification whether in the neutral wire you are getting, if 3 times frequency you are getting, then that the presence of zero sequence is there and unbalancing is there in the system. But you can say by using the passive compensation along with the active compensation in the prototype what we have developed, just you can see the compensation action. This is the load actually transformer neutral, and this is the load neutral. They are just in opposition. That's why they are cancelling to each other. That means that neutral current compensation is taken care by the transformer, right? That's why you can see the next component, that is ISN. ISN is almost zero. That means there is no source neutral current, and that is our expected response from the system. That means systems must show zero neutral current from the supply side, right? Then and only then we can claim, yes, our neutral compensation mechanism is working. And this is the wind speed we have kept here, because wind speed is not changed. We have kept here it at 12 meters per second and throughout the constant. Now in the next case, when load is fixed but wind speed is variable, and we can say again, you can see the envelope of the load current, it is not changing, but here the wind speed is changed at the same level, same instant, 7.5. And after, suppose initially it was almost 12 meters per second, now it becomes almost 14 or 13.5 meters per second. There is some change, step change in the wind speed. But what is the controller action actually? Controller action, current is increased, no doubt, because we are maintaining the voltage, terminal voltage, we are not allowing to change. But due to increased wind speed, power will be flowing more. And we know power is nothing but the multiplication of voltage and current. That's why current will increase due to increased power flow from the generator. Right. Again, these things are seen here, and we can see the frequency fluctuation. Frequency is still controlled within the limit. And this is the battery current response. Again, this is the neutral current response. and source neutral current is 0. All these things are maintained, only speed is changed at 7.5.
Sir, excuse me, sir.
Yes.
I have a doubt, sir, in this. Sir, here this ICAB means it is like nothing but inverter currents, no, sir? ICAB.
Yes, compensator.
Sir, this is supplying harmonic currents or sinusoidal currents, sir, generally?
Yes.
Which
Harmonic
currents it
current.
will?
That's why you can see here saddling points. Saddling points are coming in this current. These
Actually,
saddling points.
Sir, my basic doubt is we are generating the pure sinusoidal reference signals, no, sir? Like you said in the previous control algorithm.
Yes.
And we are comparing with the actual currents.
Yes.
So the inverter, how it will generate harmonic currents or sinusoidal currents? That is my basic doubt, sir.
Yes. Actually, there are two kind of control. One is direct control and second is indirect control. What we are doing here, we are doing indirect control here. In the indirect control, we are generating indirect reference for the inverter. That means from the supply side, comparison of the supply current, we are deriving the switching signals for the inverter, right? For direct control, we will compare the actual reference current with the compensator current. That's why in that case, you will derive that modulating signal directly by comparing the compensating current. But in this case, what we are giving, we are calculating reference from the supply and we are generating switching signal for the inverter. So basically, inverter will always supply some kind of harmonic currents in the compensator side, right? Because it is 3-phase 4-wire system, it looks like sinusoidal current, but there are saddling points and it will never be a sinusoidal current. Compensator current will never be a sinusoidal current. If you see the 3-phase 3-wire case system, definitely you are going to see like moon, the shape of moon, like here, then reverse moon, then again, this kind of current you will see here, right? But in this case, you are getting this current with 1 or 2 saddling points over the top of the sinusoidal. It depends which harmonic, because we are compensating third harmonic current separately. In this case particularly, there are two things. If you see the system model, the results is shown for this case. You see, this is the case for which we have simulated. This transformer is used to compensate the third frequency components, right? That's why we are only compensating fifth component. Major component in the harmonics is fifth component, and fifth component is compensated by the active power filter, and all the triplets are compensated by this transformer. That's why you are getting that kind of component. Are you getting my point?
Yes, sir. So that is when we use for non-linear load, sir, I think.
Yes. Current is, you see, load current is this one. Load current is almost, you can see here, it is almost by the shape of this current, we can guess what will be the level of harmonics, almost 30%, near to 30%. If it is a straight line DC, the harmonic level becomes 48%. But if this kind of the shape is there, if you are continuously working in the lab and observing the DSO, according to the wave shape, you can guess what will be the level of harmonics, right? All these things depends on the
can we use the same thing for linear load, sir, instead of non-linear?
Yes, definitely. Linear load can be connected, but the thing is, in the linear load, basically there will not be the distortion level. Current may be the sinusoidal in nature, but you can compensate the reactive component part. You can improve the power factor in that case.
Okay, sir. Thank you.
Load balancing is the another part. We can do other things. In the non-linear load, because distortion is the major parameter, we have to maintain supply sinusoidal. Now you can see the load current nature and supply current nature, and then compensator current nature. If you add this current and this current, you will get the perfect sinusoidal current, because KCL is always valid.
Yes.
Now you just see the harmonic spectrum. Yes? Any question?
No, sir. Please carry on.
Okay. Thank you. Now you can see the harmonic spectrum. We have plotted it. This is the 32.25%, 32.25% in the load, right? This is the spectrum of load current. There are 5 cycles shown here, and the TSD level is almost 33% or 32%, we can say. Now just you see the supply current 3.54 and supply voltage 0.77%. In the supply voltage we are assuming that it is perfectly sinusoidal. There is no major harmonic distortion in the supply side, right? But the important thing is supply current. We are maintaining supply current distortion despite the load current distortion 30%. We are maintaining supply current distortion within less than, that means within the limit of 5%. That is IEEE 519 is standard, right? You have to mention here why it is correct, because IEEE 519 is standard at distribution power system level. They have assigned the value of TSD, what should be the permissible limit. So by this way we can see here, and these are the some simulation results for wind solar based DG. That means this is the case where this is the this is the case where we are working, and generator, this PV array, they are connected from the load, and PV array is connected at the DC link of this inverter unit, right? So for this system there are some simulation results. My intention is to show something to you for your awareness so that you can proceed in this direction. And that's why I took both system. In one system only wind system was involved, only wind generation was involved. In the second system where wind and solar both are working in the DG, and here we can see the various parameters of the control, because here we have used some controls. Just I am not disclosing that control because it is still under progress in the publication. Just I want to show something here. But please forgive me for not showing the exact control algorithm what we are using here. But things can be seen here. This is the maintenance of the terminal voltage VT. This is the, that means in the load in this disturbance is created, but still VT is maintained. This is the templates. We are generating UPA and UQA generation. IFP, IA current is also calculated here, estimation of angle. So all these things we can see, and just you can see the dynamic performance of islanded microgrid during variation in the wind velocity and solar intensity as well. Here the wind is changed, and we can see this is basically 3-phase 3-wire system. Actually this is 3-phase 3-wire system, not the 4th wire, right? How we have maintained the voltage profile, how we have maintained the current profile, how we have maintained the, we can say, compensator current. This is the load current, and the important thing is frequency and voltage. They are these two parameters basically closely monitored, and we have controlled this. And these are some results which are showing change in the insulation level. Solar insulation level is changed from 900 to 600 level, and all these things are measured over here. Basically change in insulation, but there is no disturbance in the current of the supply side, right? And these are the disturbances created from the load, and whatever the effects are seen over the charging of the battery, right? We can see here. So these things we have simulated. One of my PhD student has simulated this, and all these things just I am showing for your reference, right? And comparative performance of 4 control algorithms. Control algorithms are mentioned here, but steps we have not shown here for the sake of just you can understand. These things are given here. And finally, we can compare which kind of response, which control algorithm is faster in this particular case, right? So this is the one reference for you how to proceed in your work, how to start your work. Now, this is my published result. We can explain here PG PL and PB. PB means battery power, PL means load power, and PG is the generator power, right? And how they are dynamically mapping to each other. Suppose generator is running at constant speed. The general assumption is generator is running at constant speed, and there is no change from the generator side, but you are changing the load according to the battery. How battery is responding to the changing loading conditions, you can see from these three graphs, right? Battery is controlled, and battery is providing backup to the increasing in the demand. This is dump loading condition, battery current, battery voltage, SOC, etc. You can plot here. I have not plotted much. I have taken only 3-4 things. Now harmonic spectrum, once again I have shown here for the previous system where we are working. 30% distortion is created, then 2.2% is maintained from the supply side, and this is the source current, right? 4.8% is still in control. And this is another 4 adaptive control algorithms, 4 or 5 adaptive control algorithms. You can see here, this is one control which is less PLL. VCO less PLL is used, and we have shown the comparative analysis how they are responding under different conditions. The conditions are same for this case particularly. Load is disturbed at 7.5, and the dynamic analysis for voltage and frequency is seen for all these adaptive control algorithms. This is adaptive vectorial filter. This is the Lorentzian adaptive filter, LAF. This is the non-linear adaptive Volterra filter. This is the momentum list, LMS, and this is the VCO-less PLL. So these are the 4 control algorithms. These are already published by me in IEEE Transactions and IET Generals. You can see in my publications also, these things are given. And this is one we can say comparative analysis is provided over here. Which algorithm is effective in which case, right? Suppose this is the sampling time. Sampling time is also one important criteria. Suppose if your control is taking much more sampling time, that is also not good control. Suppose here it is 60 microsecond, 70 microsecond. If some controller is working with 10 microsecond, that controller is more efficient, we can say. Any query, any question? Otherwise, now we can move towards the design and development of the DJ prototype for laboratory experiment. Actually, sir, I want to show some. Yes.
Sir, I have doubt, sir, again. Sir, you mentioned so many control algorithms, MLMS, Adeline, and these things. So can we consider these things as a machine learning technique, sir? Because you mentioned it is like a supervised learning.
Yeah, actually, that is another segment of the supervised learning. Basically, we can discriminate between artificial intelligence based control algorithm and intelligent control algorithm. There are two different things, right? Actually, we are not discussing here artificial intelligence based control algorithm. Just we are discussing adaptive control algorithms. Adaptive means there is certain degree of adaptiveness there in the mechanism, and they are adapting the input output variations. They are tracing the input out variations. That means because any control algorithm is working on the basis of feedback signals, right? If feedback signals are constant in nature, there is no need to change the adaptive weight of the control algorithm, and they are basically, then in that case you can use classical as well. Classical will may show same efficiency as compared to adaptive controllers, right? But when input variations are there at the feedback level, then adaptiveness must. Otherwise, dynamic behavior of the control algorithm, steady state error, covariance, all things will come into picture. So this is not the actually there is one thin line between adaptive controllers and machine learning based controllers, right?
Sir, how to choose any particular algorithm, sir? I mean, how to identify which algorithm suits for our system?
That is very difficult question. This is always difficult to answer actually. You have asked one question that is very nice question, and that is very difficult to answer as well. The reason is, yeah, actually
as I'm a new, I am asking because I need to have one partner, sir. That is the reason I'm asking.
Yes. I understand. But the thing is, unless and until you are not working on the characteristic of the control algorithms, right? Suppose this actually the answer of this question is dependent on some degree of experience. You must have some working experience in the control domain, and then you must have some statistical understanding of the control algorithms. Suppose you are understanding well what is covariance, how much covariance is there under steady state, what is the steady state error, how error is calculated. Suppose your system, sometimes what is happening, your system is not so much sensitive to the variations, then you can take any control algorithm. But some systems are very sensitive to the state variations, right? And you cannot allow any variation in the current state. Suppose voltage and frequency is very sensitive. Some loads are running with generator, and loads are very critical. Suppose you are running your lamp load, then there is no need to use advanced controllers and advanced control algorithm. But if your load is critical load, where frequency and voltage variations you cannot allow beyond 1%, then you have to go for sophisticated control. Otherwise, what is the need of machine learning based control algorithm? What is the need of artificial intelligence? What is the need of all this, right? If the reason is day by day, demand is increasing. Day by day, the necessity of loads are increasing, right? Some critical loads are coming into market. They don't need any kind of supply fluctuations, all these things, and that's why these things are suitably chosen. But still, I have the same question I have asked with so many people I have discussed. Which control we can say this is the most suitable control for this application? People always answer like this. Nobody can say this control is going to work for this application unless and until you are not applying it. That is one important thing. If you are applying, then only you can say yes, either it is working or not. It is like the giving tablet to the patient, and before giving the tablet to the patient, you cannot say either this tablet is going to work efficiently or not. That way we can answer you, dear. But the thing is, a lot of things are working on the experience, right? You have to go in the mathematical analysis, you have to go into the small signal domain analysis, you have to go into the we can say Nyquist or Bode analysis, you have to study the stability, you have to calculate the covariance, you have to calculate the, that means steady state error with the variations of input signals. That means there must be some working required. Without any working, you cannot say this will work or this will not work. This is my answer.
Okay, sir. Thank you.
Generally what happens, the people who are working in this kind of domain, right, in the research, what we are doing, we are taking 3-4 control algorithms together, and we are implementing one by one, and we are observing the efficiency of the control algorithm, right? Randomly, we are not selecting the control algorithm. We are selecting the control algorithm based on some experience, based on some understanding. And finally, we are implementing all those 3, 4, 5 control algorithms. During my PhD, I implemented 15 control algorithms, right? And then I given one conclusion: for such kind of system, for this kind of dynamics, this algorithm is showing much more efficiency. And one important thing I would like to mention here, if control algorithm performance is dependent on the controllers also, type selection of controllers. Suppose you are using Microlab box, you are using advanced controllers which are costing 25 lakhs. Some people using STM32 that is costing only that means 15 to 20,000. So basically the limitation of controllers also you have to take into consideration which control is most suitable for which controller. That's why I mentioned one sampling in the previous slide. I mentioned one sampling time requirement for the particular control algorithms. You can see here, but this sampling time requirement is seen particularly on any one controller. We have not changed the controller. Controller was DSpace 1104, and we have seen the performance of LAF, momentum least mean square, VCOL, SPLL, AVF, and NAVF. And we have seen, suppose if we are reducing sampling time below 60 microsecond, build-up process was installed in the LAF, right? That means it was required more than 60 microsecond. This is not written here just randomly. It is based on the practical exposure what we have observed during my experimentation. So all these data are given like this. And now you can see NAVF is the most complex algorithm among all. It is taking almost 120 microsecond. And we can say if sampling time requirement is more, number of samples will be less, or you can say number of samples taken by the algorithm will be less, and still if it is showing more good response, or you can say better response under dynamical conditions, you can say this is the better control which is working with less number of samples. So this is one idea you can get from here. Now, I would like to discuss design and development of the DG prototype for laboratory experimentation, how to emulate our system in the laboratory. So basically, I am skipping these parts, mathematical part. Things are not required here. And some design things I would like to discuss. Suppose we want to design one wind energy system where turbine is required, generator is required, and other PCC components are required. The switch is required, temp load is required, battery is required, loading is required. So basically how to design entire system. Yesterday somebody was asking me what should be the rating of the different components. So today I would like to discuss what should be the rating. Here these components are involved: turbine design, induction generator design, interfacing inductor design. Yes, you cannot put the random value of this ripple filter, right? That's why proper design of the inductor is required, design of VSC is required, design of these transformers. Here it is not shown, but design of transformers are required, battery backup requirement is required, design is required. So all these components we discuss here in brief, not in detail. Turbine design, there is one basic formula, PM equals to CP1 by 2. CP is nothing but power coefficient. This is very basic formula given in all books of the wind energy based systems. This is the tip speed ratio lambda, omega R by V omega, and this is used here. Lambda CP is dependent on lambda and beta. Just by keeping the coefficient over here, we will design the radius of the turbine blade. Suppose we can see here for the requirement of 2.2 kilowatt, 2.2 kilowatt generator, what will be the wind, that means blade of the turbine? It will be almost 1.434 meter. Now, how to calculate this? So you have to do reverse engineering, right? Reverse engineering is done here from generator towards the turbine. So basically mechanical input depends on the efficiency of the generator. Divide by efficiency, you will get this much watt. Assuming 10% mechanical loss in the gearboxes, we will get the turbine output power. Once turbine output power is known, you go back and put in this equation PM, you keep here and calculate all other parameters are known. Suppose rho is the air density 1.2 something, right? Pi is pi, V omega, you can decide what is the wind velocity, and CP lambda curve will give you the value of optimal value of CP. Generally it is 0.8, I think so. And R, some mechanical design considerations may be involved, but here the calculations are given very simple. The reason is we were calculating the radius of the windmill. How we have to design the radius of the windmill, what should be the tilting angle, all those things are not considered for the sake of simplicity. Just here considered what should be the axial length, what should be the area of the sweeping of the windmill. So this is the calculation, and we are calculated here R is equals to 1.434 meter, right, by giving the values of all those coefficients. Now design of interfacing inductor. This is very well known formula given in the literatures. LF is equals to √3x VDC by actually it is 1.2 K FM IPP, right? K means nothing but this is the overloading factor, generally considered as 1. FM is the frequency, modulating frequency, and IPP is the peak current ripple, right? And it should be the 10% of the current which is going from the compensator. That's why IPP calculation is dependent on the switch rating. That means how much rating of the switch is there. That's why you have to calculate the current rating of the VSC, then and only then the inductor rating can be obtained. Inductor value can be obtained. That means you can see here entire operation of the system is correlated by somewhere, right? LF you cannot keep directly. LF is this formula, and IPP is one major component. That's why before calculating IPP, you have to calculate the VSC current for the current ripple. So how to calculate the VSC current? Again, I have given here by considering the SEIG is running with VSC. So basically, it is given that 140 to 160% of the reactive power to supply the rated power is required by SEIG. So suppose, for example, 2.2 kilowatt and 3.5 kilowatt load. This is the load rating. First of all, you have to decide the load rating. Accordingly, again, reverse engineering starts. To supply this rated power, a 2.5 kilowatt capacitor bank is also connected at SEIG terminal, right? For exciting the generator. In that case, VSC has to supply deficit reactive power, that is 1 kilowatt to the SEIG bus, and therefore rating of the VSC becomes 2.5 kVA. In the morning, Professor Fernandez was also telling the rating of the VSC must be in kVA, that is 100% you can say true. It is calculated based on the kVA rating. Now the VSC current is given as follows: VSC equals to VL ISC. Now VL is known, line voltage is known, capacity, short circuit capacity of the VSC is given. Now we can calculate, we will have the IVSC, and IVSC is almost here 10 ampere from all these calculations, and then 10% of the VSC current is required as a peak current to current ripple, and 10% of this 10 ampere becomes 1 ampere, right? So by this way, you are keeping 1 ampere over here, and FM we can take 5 kilohertz, overloading factor, then modulating index, all these things. VDC level is nothing but 1.6 times higher from the AC side. So LF can be calculated just by putting all those values over here, and you will get how much? 4.48 millihenry. Then we during the simulation you will keep 5 millihenry if you are working with 230 volt line to line system, right? If you are increasing line voltage, accordingly current will change, VSC current will change, then peak ripple current will also change. That means you just see, if you are changing the line voltage, the same inductor value will not going to work, right? That's why these things are very much important as far as proper design of the system is concerned, and we must understand all these things. Now selection of battery energy storage system, how to design our battery storage, then its capacity is dependent on the required amount of power used as a backup and storage. The voltage at the VSC, I just told 1.6 times it must be. Then finally you will get the battery voltage 2√2 by √3x VL. Just by putting the line voltage, you will have the battery voltage backup. Suppose for 240 volt, 396 is the exact value coming. You can select 400 or next higher value of 396. And there are two things in the battery. One is voltage rating, another is ampere hour capacity, right? Suppose what should be the ampere hour capacity? Suppose if you want to generate 1 hour battery backup to the entire load without any contribution from the generator. Here, keep in mind generator, load and battery is there, right? The kilowatt hour calculation is dependent on this calculation, total kilowatt into hour divided by this. So this much kilowatt hour is required, then ampere hour becomes this divided by voltage. 9.1 ampere hour will be the value, and finally you can select 12 volt 7.5 ampere hour, because 9.1 ampere hour may not be available in the market. Then you will take 12 volt and 7.5 ampere hour. And for making it 420 volt, you have to connect the strings of the cells, right? 35 units we can connect for making it the desired voltage level. Design of star delta transformer is also needed. This is simple design, we can do it. These things already covered. And this is these components are required for making a prototype. This is we can say this is the D space component, that is the major part of this entire system. DSO and all the DC batteries are required. And this is D space, that means control desk, terminal is there. And this is the emulator of the wind, ACS550 drive. This is the generator motor. And all these things are connected. Inductor, ripple filter, you can say here, this is the ripple filter, this is the transformer, and things are arranged in terms of load over here. This is the inductor load for making the distortion level high. This is the power quality analyzer. This is the sensor circuit. There are 3 story here. 1, 2, and 3 DC link is there. DC supply is there for supplying to the sensor circuits. Sensors are designed over here, and this is the inverter block over here. Inverter block is there. We have compiled, and all these things are running in better manner. Everything is taken. Now you can see the details, detailed photographs. This is the D space. There are actually 8 ADCs and 8 DSCs in this D space, right? And 4 are muxed and 4 are not muxed. ADCs are, and the beauty of this D space is basically ADCs are working, sampling in both directions. That means there is no DC offset required for the D space. If you are working in the STM32 controller or ARM Cortex, you have to add first DC offset for making entire signal above the x-axis, and then again in the programming you have to take care about, you have set DC offset from the external side. But in this controller there is no need to DC offset. Work will be done, that means sampling will be done in both directions by the ADC of this converter, and that provides the flexibility. Other flexibilities are you can make online tunings, online control, monitoring, corrective actions, everything can be taken with this. While in the basically microcontrollers, every time you have to make your system switch off, and then you go into the programming and change the program, and then again you run. That means during the on time, during the running time, you cannot have that kind of flexibility which is provided by the D space. That's why it is costly. It is almost costing 6 lakhs, 6.5 lakhs. And this is the inverter unit. Basically, there are 4 legs here, and these are the IGBTs arranged over these legs. Right? There are few things for interfacing required, like deadband circuit, optocoupler circuit, all those. This is the battery block. Right? All these things are. I'm skipping the procedure for the sensor design. And these are the results, performance, where we have tested the simulator, that means prototype developed system. And we have seen here, despite the load current nonlinearity, supply side is purely sinusoidal. You can see the compensator current over here, and you can see after disturbance also, there is no disturbance in the supply voltage. Battery current, load removal, ICA, and you can see here at the T junction of the connection where loads, compensator and supply, they are connected, and after disconnecting the load part, supply and compensator, they are equal, right? That means naturally what is happening here, ISA is always equals to ICA plus ILA, according to the Kirchhoff's current law. And ILA, when ILA is 0, ISA becomes ICA. So all these things are verified by the basic fundamental rules of the electrical engineering. And because sometimes if you are claiming yes you are correct, but if your results are not following the fundamental rules, results will not be considered as a correct result, right? Here battery charging discharging is shown according to the load variations. Suppose you are inserting load over here, you in the another case you are rejecting the load. Battery terminal voltage is almost maintained constant by the controller. Only thing is battery charging currents are changing, decreasing or increasing, right? So by this way you can understand how the system is functioning. And this is the neutral current compensation we have seen in the designed prototype. These are exact in phase opposition. You can see here. That's why source neutral becomes 0. And this is the balancing at the terminal, generator terminal. ISA, ISB, ISC currents are balanced in nature. VSB and VSAB, these are line currents. Voltages profile you can see here. Just if you see closely, you will get the 20 millisecond per cycle. This is the 20 millisecond per division. I have written here. On the x-axis, 20 millisecond is the per division time, right? You are getting here 20 millisecond per cycle. That means frequency is throughout maintained. Though variations are there from the input and output side. These are the variations seen from the input side. Voltage profile you can see here. Voltage is not disturbed and due to variation in the input parameters. These are the steady state results we have seen here. We have maintained the 3.1% harmonics level in the supply current despite 34.1% level in the load current. We can see the effectiveness of the control algorithm, and this is LAF control algorithm we have implemented. And these are the references. We have the publications and thank you very much. Now I would request Sombir to show some simulation to you all people. If you have any doubts, you can discuss. Any question, any query from the participants? Hello.
Yes, sir.
Participants are not there. Participants are there. Participants are not asking.
कोई रिस्पॉन्स नहीं कर रहा है सर.
हेलो.
रिस्पॉन्स नहीं आ रहा सर, किसी का ही बोर हो गए लगता है सारे.
Participants are requested to ask your queries. Just raise your hand. Sir, can I hear me, sir?
Yes, Dr. Sundaram, yes, go ahead.
Sir, it is a very state of art work. Congratulations, sir. It is very nice and informative session. But sir, I have a simple doubt. Can we change that sigmoid function to another function for that aspect that you are using 1/1 plus e raised to something?
Yes, dear. Actually, there are variety of activation functions, sigmoid function, even exponential functions can be used. But the thing is, sigmoid function is considered as the most efficient function because it is not creating any kind of non-linearity in the weight calculation. But instead of sigmoid function, you can use variety of functions. There is no issue in it.
Yes, sir. Thank you, sir. Is there any effect on the controller aspect?
No, not at all. I don't think so.
Okay, sir. Thank you very much. It is very nice and very informative session, sir.
Thank you very much, Dr. Sundaram. Any other participants? You can make the interaction, please. I am waiting for your questions. All are listening me. Please, just my one request is you turn on your camera. Otherwise, we will not consider the attendance of this session. अगर आपके कैमरे टर्न ऑन नहीं होंगे तो आई फील यू ऑल आर एब्सेंट. देखो, the people who are listening me, please turn on your camera so that physical verification can be done. Because this was my own session, I want to verify whether you are attending physically or not. If you are making your camera turn on within 2-3 minutes, I assume that yes, you are there. Otherwise, you are just connecting and going. Yes, someone has raised the hand. You can ask directly. All are enabled, I think so. जबरदस्ती क्वेश्चन भी पूछवा रहा हूं आप लोगों से. कोई बात नहीं, अभी तो सब ऐसा ही चलता है भाई. My intention was to make you aware how to use different control algorithms in the distributed power generation system. What is the difference between adaptive controllers, classical controllers? Someone has asked about machine learning based control algorithms. Still I am entering in that domain, but till today I have not implemented any machine learning based control algorithm. That's why I have not that much expertise as I have used adaptive controllers. So you all show some interest to learn something. You can implement, you can collaborate. If you have any doubt, if somebody is doing PhD or somebody has done PhD, you all are welcome to ask query. I will be happy to answer to best of my capacity and knowledge. Okay, otherwise, Sombir, you just show simulations. Still we have 10-12 minutes remaining. You show some simulations, how to start the simulation, how to proceed in simulation, and then we will have a small tea break, and the third session will start at 3:45.
Sir, can we turn off our camera?
Yes. Good. You can.
Hello everyone, myself Somvir, PhD research scholars at DTU under the guidance of Dr. Ashutosh sir and Professor Madhusudan Singh. And that is the symbolic representation. Sir, screen visible?
Yes, coming.
Yes, sir. Okay. That is the symbolic diagram of a standalone hybrid wind solar system.
You show component by Sombir. You just show them component by component. Just open the PV system. What are there in the PV system? Then open the generator. Suppose SEIG.
Yes, what sir, sure.
Right?
Yes, sir.
Everything, so that they must have some idea.
Basically, sure, sir. Yes. In this system, basically, we have wind turbine, PV system, battery system, voltage source, converter, and filters, and linear or non-linear loads. So we'll start from wind turbine. That's the section of wind turbine. That is tap input, and the wind speed is at 12 meter per second to 14, 16 or 18. We can assume. Yeah, we will take. And that is the induction generator and its parameters. And that is the ratings of a wind generator or SEIG induction generator. Basically, this is 5 HP generator and 3.7 kilowatt, 415 volt, 15 hertz. Stator resistance, inductance 1.405, 0.0078 Henry, and inertia and friction factor. And that are the biaxial conditions 0.803330000. That are the simulations parameter of SEIG. And that is the reactive power support. which is taken 4,200, and that selected section is the wind section, and that 1/70 value, that is gain, that is the gear ratio, and that is wind speed, and this is the wind generation diagram. This diagram is already present in Simlink. That is the wind turbine section, which is coupled to a induction generator. And next section is our PV system. This is PV system. In this PV system, we will use incremental conductance technique for to extract maximum power. That is the Simulink diagram of this technique. This technique, pulse generation, that is IGBT section, and the inputs are given step. The initial value 900. We can vary this solar insolation level 900, 500, 400, any value, and that is the temperature section. We can vary also in temperature for any value, and the capacity of the PV system is 2.16 kilowatt. That are the results of this section. I have plotted on fixed values, and that is the variation in duty cycle. That is voltage VPV 203 volt and 10 ampere current, and that is universal bridge. And this section, in this we use 6 IGBTs, voltage source converter, and this is the fourth leg of the IGBT, which is used to provide neutral compensation. That are the inductive filters. The values taken of the inductive filter is 5 micro Henry to 6 micro Henry, and that are the measurement blocks. This one. This blocks is used for the source voltage and current measurement, and this block is used to measurement the compensator voltage, and this block is used to measurement the voltage and current of the load voltage and current, and this is load. Linear and non-linear load is applied in this section, and that is the control part. In this control section, we have implemented DROGI FLL control. FLL is frequency local loop technique, and DROGI stands for dual reduce order generalized integrator. And this technique is used to extract the fundamental load current component, which is further applied in this to improve the power quality of the system of the standalone hybrid system. And that is the VT calculation and unit temperature generation part. In this section, we use the source voltage for the generation of peak voltage VT and for the unit temperature generation UA, UB, and UC. Further, the VT calculations, that is the error, that is the reference voltage 330 volt. The comparison is given to PI controller, and the IQ value is taken, and that is the phase shifted or quadrature phase unit template generation, WA, which is 90-degree phase shifted. That is quadrature, and that is the phase unit template generation. Further, the outputs are given to the sample and hold circuit and real and this section is the inputs are given the real part or in phase unit templates जो हमने generate किए हैं and the PV current are given. Further, similarly the quadrature part, and the further this part is utilized to generate the reference current for the generation of switching pulses. And the upper side we use the 50 Hz frequency, the reference frequency, that is the source frequency. Further the output and the comparison is applied to the PI controller, and its input is given in the active template generation, and that is the below part is quadrature unit template generation या reactive power generation, sorry, the quadrature template generation. Further this part is used to generate the reference current generator, and then the comparison of the source current and the reference current generation is used to generate the switching pulses for the VSC, and further the switching pulse is given to the VSC. This output is given to VSC, that is to control the VSC. Next, that is the DC link where the PV system and the battery storage system is connected. That is the diagram for the battery storage system. You can see the configurations that are taken. Lead acid battery 500 volt है, 7.5 rated. ये जो initial state of charge है वो 40 है. Battery response time is 30 seconds. That values are taken. And further the battery storage system is utilized to active and reactive power support during the intermittent or dynamic conditions of solar and wind and unbalanced loading condition. And that are the results on fixed wind speed and fixed PV system जो हमारा है उसके अंदर result and fixed load voltage. You can see these results. I will zoom it. Frequency is vary between 49.99 to 50.1, and that is the VABC is the source voltage, and IABC is the source current, and IL is the load current of ILABC, and fourth one is the compensator current, ICABC. Compensator current, and that is the frequency, and ISN is the neutral compensation current. VB is the battery voltage, which is 500 volt, and IB is the battery current. Here is some value, we can see that. Yes, that are the results on fix. That from my side. If anyone is asked something, you can ask me freely.
Sir, can you explain how the active component is generated?
Yes. Sure. This is the part for the active component generation. In this we will use the control algorithm D-Rogi FLL. Here the inputs is in phase, and the quadrature unit templates outputs is given to ZCD. Further the output of ZCD is given to sample and hold circuit. Further this part is used to generate the active component ILFA, that is active component, and the below component ILFQ is the reactive component.
Sir, how this ZCT and sample and hold will generate, sir? Can you please explain in detail?
Generation. Further data are given in MATLAB. We have take the values, but nothing to set. That's value are taken from directly MATLAB Simulink model. But we have sampling time taken TS, and the initial conditions is taken 50, both sample and hold. That is the real part, which is directly taken into MATLAB, and that is the part, absolute value. Yes, anyone?
Sir, where the pulses are coming, sir?
Pulses, that's are the pulses. Yes, that one. That are switching pulses are given to VSC directly to control the VSC.
So my doubt is pulses are coming from where? Can you show it?
Yes, sure. That's pulses generation. The pulses are generated by the comparison of the reference current and source current. That one.
Sir, can you explain this operation for understanding purpose?
Okay. Directly the IS is the reference voltage, and where to this one is the reference voltage, and this one is the source voltage. And then the further we take from a DMAX and the phase A current hai, and this one is the phase B current, and this one is the phase C current. Similarly, in the source current, similarly the phase A source current, phase B source current, and phase C source current. And the comparison of phase A, B, and C is given to the relay circuit, and the switching value is taken 0.1 to minus 0.1, and when the relay is on at on 1 and off on 0, similarly the value is taken. That is the Boolean data expression. Similarly, that value is taken from MATLAB, and the NOT gate is applied for the switching pulse. We are given to 135 and 246 in the VSC, and then the switching pulses are generated and that are directly given to the VSC. Also, I will show you the switching pulses or gate pulses. That are the switching pulses, and that value is very 0 to 1 unity. Wait, that are the switching pulses. Screen is visible?
Yes. Thank you, sir.
Yes. Any questions from participants side? Anyone asks to something? Yes, participants. Any question?
Participants, you can interact directly with Sombir Kundu. He is working on
Sir,
these
what about
simulations.
power measurements?
Yes.
Measurements. Can you show power measurements, sir?
Yeah, sure. That is the load voltage, source voltage, and the PV voltage and current. That is. These results are taken fixed wind speed and fixed PV power, a solar insolation, and fixed load.
Somir, I think so.
Yes,
You have displayed all the simulations wonderfully for the participants.
yes, sir.
I am very much
Thank you so
thankful
much.
to you for accepting my
Sir, one
invitation in
doubt,
very
sir.
short notice.
Thank you, sir.
Hello,
Thank you.
participants.
Sir, one doubt, sir. One doubt.
Yes.
Yes.
How to select this sampling time, sir, here in and switching frequency related to the sampling time.
Asutosh, sir, please give answer.
What is he asking?
How to select the sampling time? That is 50 microsecond or 20 or 10. That is asking.
That is correct. Actually, you see, that will depend on your MATLAB capability. Suppose you are working in 2009 MATLAB version or you are working with 2019 MATLAB version. If you are working with 2019 MATLAB version, minimum sampling time 10 microsecond. Below that, you cannot go because number of samples it will not be able to handle. Suppose for this case, I think so. In which version, Sombir, you are working?
Sir,
2018?
16A.
Huh?
16A.
16A. Actually,
Yes, sir.
Somir is working in 16A. Accordingly, he has taken less number of sampling time so that samples may be increased. Actually, you see, your quality of result is very much dependent on the number of samples taken by the control algorithm. And sampling time, if you are selecting less per cycle sampling time, it will create more sample. If you are taking more sampling time per cycle, it will create less number of samples taken by the control algorithm. Actually, all the processing will be done in the control algorithm, sample by sample, right? And finally, aggregation is done at the end of the last stage. So that's why sampling time is playing a very important role. But what I observed during my work also, sampling time you cannot reduce very much in lower version of the MATLAB. If you are working with upper versions, you can take even 5 microsecond also, right? Otherwise, what will happen? Suppose in 2009 version MATLAB, if you are taking 10 microsecond sampling time, it will run for 2 hours. If you are clicking the simulation run, it will run for 2-3 hours. Then it becomes very boring actually. You will not get anything and you will lose your interest. That's why again the answer is same. It depends on operational efficiency of the MATLAB, and but the important thing is you always try to reduce your sampling time so that you will get quality results with less number of sampling time. Any doubt, any question? Yes, now we are running short of time. Dear Sombir, you have done wonderful job by presenting your simulation in front of participants.
Thank you so much, sir. Thank you so much.
Being a participant of this FDP, you have done very wonderful job because you are attending FDP throughout the day, and at very short notice you have taken the challenge to show the simulation. Entire team is very much thankful. Now I would request Ammi madam to wind up the session.
Thank you very much, Giri sir, for sharing your expertise in the field of wind solar-based standalone distribution generation. Thank you so much, sir.
Thank you very much, madam, for your gracious presence here.
Sir, but really, it's a very nice session, even though I have enjoyed this session.
Thank you very much, madam. Thank you. And now, participants, we will meet again at 3:50. Please take a nice tea and with full refreshment and energy, you again join the third session, last session of the day, and try to interact with the expert. He has done PhD from the SVNIT Surat. He is also very learned person in this domain. You all are requested to join once again after the tea break. Thank you very much. Thank you, Ami madam. Thank you, Sombir. And thank you all organizing team members. And we will again join. Thank you. Ami madam, and now you have to take care about the third session.
Sure, sir. No problem.
Okay. Thank you.
Okay, sir. Good evening, Mehta sir. Hello. Am I audible? Good evening, Mehta sir. Welcome, sir. I think sir's mic is muted. Welcome, sir. Hello. Dr. Hitesh Mehta, sir.
Good afternoon. Yes, I'm here.
Good afternoon, sir.
Are you able to see my PPT?
Yes, sir. PPT is visible.
So whenever you tell, I will start my session.
Yes, sure, sir. Very good evening to one and all. On behalf of organizing team, myself, Dr. Ami Patel, heartily welcome to Dr. Hitesh Mehta, sir. Today, I am very much happy to introduce our eminent speaker, Dr. Hitesh Mehta, sir. Sir has received his B in Electrical Engineering from Ali College, Morbi in 1997. MTech in Electrical Engineering with specialization in power electronics and electrical drives, and PhD from SVNIT Surat. Sir has joined Department of Electrical Engineering, SCAT Surat, as a lecturer in 2001. Presently, Sir is an associate professor at Department of Electrical Engineering, SCAT, Surat. Sir has authored and co-authored more than 15 research papers in reputed journals and conferences such as IEEE Transaction, elsewhere AIP, JPB, conference, etc. He is also serving as a potential reviewer in various reputed journals such as IEEE Journal of Photovoltaic, Renewable Energy Focus, Journal of Emerging and selected topics in power electronics, applied energy, etc. Sir has also soldiered various academics and administrative portfolios at college and university level. Now I would like to request Dr. Hitesh Mehta sir to continue the session. Please, sir.
Professor Ami, for a very well this introduction about myself. On behalf of SCAT, first I want to thank Dr. Ashutosh Giri, the coordinator of this event. I want to thank Dr. Sanjay Joshi, principal of GC Baruch, even Dr. Vishal, for giving me such a good opportunity to talk with researchers and teachers on this online platform. Thank you very much. My today's topic, am I audible, Professor Ami?
Yes, sir, you are audible.
Okay, fine. So today's topic of this is a 3-point model-based MPPT control of PV system. So that we are trying to explain, it is a new algorithm developed with a very less time. The people will get a directly maximum power point of any PV system, whether it is a single module or maybe it is a PV array, whether it is a normal atmospheric or maybe in a partial shading. So everything we will try to cover whatever the time permits in this particular session. Okay, in between, if any participant want to just know about the things, you can interrupt me so I can explain you and I will share whatever the knowledge I have with you. Okay. So the first slide represent the outline of today's presentation. We'll start with some basic introduction. Then we'll go directly to the 3-point model. Then we will see the simulation studies, whatever we have done for this. Then we will try to understand illustration of the 3-point model MPPT through experimental study. And then I will summarize whatever the points we discuss and will show you the publication. If somebody wants to refer this work, they can refer that paper and you can contact the authors, or maybe the new knowledge you will get and you can implement whatever the things advisable in your research area. So everybody know that a PV device is nothing but a PN junction diode. So if you see here, as an electrical engineer, we know everything we can convert into the equivalent circuit. So PV cell is converted here into the equivalent circuit, that is called a single diode model equivalent circuit of PV device. There are so many equivalent circuit, 2 diodes, 3 diodes are there, but generalized form, all researchers are using the single diode model because it gives the accurate model of the PV junction diode as a PV device. Okay, so PV device will give you the electricity when light falls on the particular area. So here an electrical output of a PV device being strong function of the climatic condition. So very important thing, those who are working for in a PV area, this irradiation, or maybe the word we are using is insolation, that is G and T are very two important parameter to track the characteristic of any PV cell. So this is represented by here the single diode model as an electrical circuit. The single diode model reproduces highly accurate output characteristic of different kinds of PV device in any climatic condition. So this is the reason that we are just referring the single diode model to get a characteristic of a PV cell. In the PV system analysis, the single diode model is mostly preferred as it has a less number of parameters and less computational complexity. This is very important statement, that whenever the number of variables are more, when you go for solving that particular equation, it will take more time. So this single diode model is having a less parameter compared to the others equivalent circuit. So it is shown in figure 1.1 where the current and voltage is defined. You can see here, this is a current and this is the output current. What are the things we will see in the next slide? And this is the output voltage we are getting. The another two things are represented by series resistance and shunt resistance. What is the important of this that we are going to learn in the next slide. And then there is a I0 also. And this all is represented by what is I is equal to with this. IL is the light current. Okay, IL is the light current. So we are getting this equation. Yes, there is another lectures I need, suppose sometimes maybe you'll familiar how to find out the parameters of this equation. That also we have done in a very simpler manner. There are so many methods available to find out the parameter, but we will accept this is the equation of your PV cell. Okay. Here you can see there are different IV and PV characteristics I have shown. So this is the equation number 1, that is a basic equation, and as I told you, the things are given here about the nomenclature. So IL is the light generated current, I0 is the reverse saturation current. Why? Because we use equivalent circuit as a single diode model. So it has reverse saturation current, RS is the series resistance, RSH is the shunt resistance, N is the ideality factor. Even there are a research to find out IL, I0, RS, RSH and N for different PV cells. Okay, so there are so many methods available, but sometimes if we will get a chance, we'll discuss for that. So according to the equation number 1.1, a set of 5 parameters identify the IV relation. What does it mean? If you know IL, I0, RS, RSH and N, you can draw the characteristic of current versus voltage. So that is called the IV relationship of the PV cell. Okay, but for that you need the knowledge of these 5 parameters. Okay, so according to equation number 1.1, I is an implicit function of voltage and current. Implicit means implicit means I is a left hand side, this is an unknown variable, but in right hand side also I is there. Okay. System of equations are called implicit function. If there is a no I in the right hand side, that is called the explicit function. So why we are discussing this? Because to solve the equation for current I, you cannot directly implement the simple analytical methods. You have to go for the iterative techniques to solve this particular equation, and for any iterative process you have to assume some initial value, that is called the initial conditions. Okay, so for this equation, Newton-Raphson, Gauss-Seidel, such type of techniques you can use, but in a general way people are using the Newton-Raphson method to solve this non-linear equation. Okay, so this is the curve of I versus V. This is the curve of P versus V. So this is called IV and PV characteristic. G1, G2, G3, G4, G5 are nothing but various values of irradiance, or we can say the insolation. Same way in figure number 1.3, you can see the different characteristic for T1, T2, T3. Means for different temperature, IV and PV characteristics are shown. The motto to show this characteristic is to prove that the IV characteristic of PV cell is depend upon the 2 parameters. One is the insolation and another is the temperature. So if you see the characteristic, current I is directly proportional to G. Suppose if you compare G1 and G5, G5 is the highest value, so you are getting the highest current. But for temperature, but the voltage is very rarely change, or we can say very less change in the voltage due to G. While in case of temperature, current is changing very less and voltage is changing more. Okay, so it is a observation and proven thing that if there is a change in insolation or irradiance, the IV characteristic means current will change drastically, and if temperature is changed, the voltage will change in your characteristics. So you can see from these 4 diagrams. P is nothing but a product of V and I, because PV cell will give you the DC energy, means DC voltage and DC current. So P is nothing but simply V into I. Okay. When module receive uniform radiation, IV curve exhibits a single step, means this. But when different modules in the PV plant are under different irradiation, there are multi-steps in the IV curve and multiple pricks. So what does it mean, or what I try to explain you, that suppose in one area 10 modules are connected. Okay. So out of 10, 5 modules are getting suppose G1 irradiation, 2 modules are getting G2, and remaining 3 are getting G3. Then all 3 have a different irradiation value. Then you will not get a one simple peak. What peak means? You can see here. This is a peak. So for every 1 G, if the insolation or irradiation is same for all the panels, only you will get a one maximum peak. But when such case is there, you are getting different peaks. So this is called under partial shading condition. The short form people are using is PSD. Okay. So you can see here, but out of this all 4 peaks, one is the highest peak, that is called the global maximum power point, and another points are called the local peak points. Okay, this is the global maximum power point, another are called the local peak points. Okay, so in this condition, it is very tedious job to find out the GMPP for such system. So there are so many algorithms are developed to find out the maximum power point under the partial shading condition. Okay, but whatever we are trying to understand today, the same will work also for the partial shading equation. Okay. So another things, as I told you, so many algorithms are that I am not going in detail one by one, but these are the 2 categories of the classification for MPPT methods. So MPPT methods for uniform irradiation is left hand side. MPPT methods for non-uniform irradiation is for right hand side. Okay. So there are some algorithm, they will only work under the uniform condition. There are some algorithm which will work only for the partial shading condition. There are some algorithm which will work in a both the system. So if this is the both the system is there, then your algorithm, it is called the generalized algorithm for any PV system. Okay. So now let us start with the things that is called the 3-point model for PV system. Why we have given a name 3-point model? Because we are only considering 3 points of a IV curve, and from this 3 curve only we will develop an algorithm which will directly point your maximum power point. Okay, so that's why the name is given 3-point model. Means we will take only the 3-point values V1 I1, V2 I2 and V3 I3. Only these things are there. Okay, so propose 3-point model for the single diode model equivalent circuit. Okay, so let us start again with the same thing. This we have already done, this circuit. But here if you observe, RSH is not considered. If you observe here, RS and RSH is not considered. This is nothing but your lead resistance, the resistance of your diode are considered. So figure number 2.1a is the practical model, means we are considering all the things. Figure number 2, we are considering only the RS. Okay, we are not considering RSH. So such type of equivalent circuit is called the simplified SDM. And the third is there is no RS, no RSH, means in ideal case. So it is called ideal model. So there are some algorithm that works only on ideal model. So it is not acceptable in industry. Why? Because never you will find any ideal condition in any real-time application. So if your algorithm works for the practical model, it will be implemented actually in the field. Okay. So the practical model represents the accurate performance of the module equation 2.1. Define the relation between the output current and the output voltage for the practical model. So this is very important when you check your particular algorithm, what we are trying to develop, it should run on practical model also. Okay, so let us start. These are the mathematical step. I will try to explain you in a short way, but yes, we will discuss somewhat in detail about this thing. So these are the mathematical steps. I will share this PPT, not an issue. You can see this step. So after this all, you can see here, this is nothing but we are rearranging equation, further simplifying equation of the above one, where Vt will be represented by Ns Kt by Q. Now the very important thing is I am finding out the values when I is equal to Isc. What does it mean? Let me go back to your characteristic. This. Suppose we will consider this. So I is equal to I am taking Isc. So I am considering this point. In a second way, if I will consider V is equal to VOC, means this point. So at this point your voltage is 0 and at this point your current is 0. And another point we are having, that is called VMP and IMP. Voltage at maximum power point and current at maximum power point. So that we are trying to take in our mathematical steps. Okay, so you can see here, setting I is equal to Isc, means this I we are replacing with Isc, and V is equal to 0 in equation number 2.1. So you will get this equation. Now setting I is equal to 0 and V is equal to VOC. What does it mean? We are trying to implement this equation at short circuit of your PV cell and when the PV cell is open circuit. Okay, so we are getting the equation number 2.4 and 2.5 with these two conditions. Okay, now we will substitute 2.4 into 2.3 and do some mathematical step. Solve for I0, rearranging the equation 2.6. Okay, again substitution is there, neglecting the term because it is very less. Okay, and finally we are getting this equation. I is equal to Isc minus VOC by RSH 1 plus RS by RSH e raised to V minus VOC plus IRS by Vt. Why we have done such thing? That is very important to understand. Why we have done such thing. So now if you see equation number 2.1, this is the implicit function. I is here also, I is here also. Now if you see the 2.12, there is no I. Okay. Now again rearranging the equation and finally you can see with the mathematical rules, finally the 2.15 equations we are getting in the form of only I, Isc, VOC and Vt. What is Vt? That I have given here. Ns into Kt divided by T. So these are the known values. So what we have done in 2.15, we have removed the dependency of I in the right hand side. So now it is an explicit function and it is easily solved. If you know Isc, if you know VOC, if you know Vt, if you know voltage, so you can solve it. Okay, so again, let me try to explain you why it is called 3-point model. Any doubts up to this, any participants? Okay, I think everybody understands. Now, neglecting RS and RSH in equation number 2.15 is simplified as this. So again, if you see the equation of this, if you draw the curve I versus V, you will get the exact curve of this mathematical equation. I is equal to AV raised to B plus C. So you can see here A, B and C are the three unknowns that you have to find out. So we have compared these two equations and try to find out the value of A, B and C. So in next slide I will show you that. So the three coefficient of equation number 2.17 means this equation. I want to find out this. So what I have done? So first, the short circuit points means we will make it voltage 0 and current is equal to ISC. Second point, we are making open circuit means I is equal to 0, V is equal to VOC. And the third point, we have taken VMP and IMP. So we are getting the value of A, B and C after the mathematical step is like this. So A is equal to minus ISC upon VOC raised to B. B is equal to log of 1 minus IMP by ISC by log of VMP upon VOC. C is equal to ISC. So you are getting this equation of A, B and C. If you know this value of A, B, C, by putting the value of VOC, ISC, VMP, IMP, you can draw the curve of I versus V. Now definitely some participants have a question that, sir, from where we are getting VOC, ISC, VMP, IMP. So when you purchase any PV module, in a specification of PV module, these things are given on the back side of your panel. That is called the data sheet. Correct. So VOC will be given to you, ISC will be given to you, VMP will be given to you, and IMP will be given to you. So you can find out that value from that particular panel. So no need of any dependency to perform any practical on this. The estimated coefficients are substitute in the previous equation and we can draw the IV and PV curve. Okay. So now this curve is exactly matched with particular our IV PV curve which is designed, or we can say we draw from the equation number 1, that is the actual equation. Now everybody says, okay, you find out this thing, how to validate this particular thing. So another thing we have done, that is called the parameterization. The curves of the PV module shows the curve of the PV modules we validate through these different values. Okay, so the 3-point model is validated by 4 crystalline PV modules. We have taken these different 4 panels. The one is Max 60, it is a company name. This is a Vari 160, that is again a KC 200 GT. So many papers refer this module as their what we can say the ideal module for any algorithm. Then it is a WS250. You can say I have taken a range from 60 watt, 160 watt, 200 watts and 250 watt. Okay, and these are given to you. VOC, ISC, VMP, IMP, PMP, this. So from that we have find out ABC from this equation. From this equation we have find out ABC for all this model. And what we have done, we have drawn the IV curve. How to do the IV curve? We have ABC. So in this equation I will put ABC. I will vary the voltage from 0 to VOC. So I will get the value of 0 to IEC. Okay, and we draw the curve. Okay, we draw the curve. The estimated IV and PV curve pass precisely through the 3 points given in the manufacturer and data sheet. What I am trying to tell you, if you draw the curve of IV and PV, you are getting this curve which is passing through this ISC, VMP, IMP and ISC properly as it is given in the data set. So it's validate that your model is showing the exact IV and PV characteristic of this PV cell. Be careful in mind, there is no iterative process for this. Only you have to find out A, B and C. Again the ABC you are determining from the VOC, ISC, VMP and IMP. Okay. Again, that is okay for the one case, but people will not accept your research work if you put it in a proper way. Means PV is highly dependent upon the atmosphere. So now we have tried to find out the same IV and PV curve for the different environmental condition. So the datasheet information is considered as the reference value. What we have taken from the datasheet: short circuit current, open circuit voltage, maximum power point voltage and current as a reference. These quantities are adjusted for different irradiation G and T. હવે આપણે શું કરેલું છે કે we have tried to find out the IV and PV characteristic for different G and T. So before finding out ABC, I have to find out IAC, IMP VOC and VMP at G and T. So this is already a developed equation of physics, that when temperature change, how to find out this thing. Alpha and beta is again given to your data sheet. That is a temperature coefficient for voltage and current. T reference in our case means any PV system we are taking as a 25 degree centigrade. Okay. If you go for Kelvin, it is 298. So from this, we are finding the ISC, IMP, VOC, VMP at different G and different T. Okay. Now, you can see in equation, figure number 2.3, the measure and estimated IV curves. What does it mean measured? What we have done during the research, that I have my PV module, I will connect with some resistive load and I will change the resistance from 0 to maximum, and I have measured the voltage and current and draw the characteristic which is shown in a purple round. You can see this is the actual with a signal conditioner circuit, power supply, and for this particular algorithm, I use a STM32 microcontroller. We have prepared our own DC-DC boost converter, and we connect the resistive load. So these are the front view and top view of the hardware. If you see figure number 1 and 2. See the results of the hardware. What we have done, I have implemented the TPM algorithm and P&O algorithm. Okay, so figure number 4.23a. Okay, it is nothing but a snapshot for the PV module when G is equal to 1, T is equal to 25 degree. A represent for the P&O and B represent for the TPM. So you can see simply the variation is here. There is a straight line. It will take this much time and it will take very less time. Correct. Same way for the enlarged view at initiation. અહીંયા ચાલુ થાય છે આ algorithm. અહીંયા સુધી સિસ્ટમમાં algorithm ચાલુ નથી. આ offset system. જેવું આપણે અહીંયા ચાલુ કર્યું આનો large view અહીંયા છે. If you can see this diagram, અહીંયા જે છે તે delta x 800 છે. અને અહીંયા છે તે delta x 222 છે. Means delta x is nothing but a time that I have measured from the DSO. It is a facility that you can take a time previously and the actual. તો આમાં 800 milliseconds no time લાગ્યો reach થતા. In our proposed algorithm, it takes only 222 seconds. Means 1/4 of the P&O algorithm. So this is only a simple we have checked initially with a 1 PV module. Okay. Then there is algorithm under sudden change in irradiation. પછી શું કર્યું કે પહેલા suppose 1000 છે ને પછી drastically we have taken 500 kilowatt per meter. So this is the result of P&O and our delta x છે. So if you take delta x, it is 420 millisecond to settle down for the new value, while in this case it is taking only 100. So it is again 1/4 of the P&O. એ તરત જ settle થઈ જાય. What it tried to show you that the dynamic efficiency of the system is also very good. It is also fast and it tracks the maximum power point at even in a dynamic conditions. Okay, dynamic means એક વેલ્યુ માંથી બીજી વેલ્યુમાં ચેન્જ થાય અને તરત જ તમારું અલ્ગોરિધમ એને ટ્રેક કરી અને મેક્સિમમ પાવર એક્સટ્રેક્ટ કરે. And if your efficiency is high with a less time, your algorithm is good. So that we have proved here. Okay, then this is nothing but a PV simulator IV characteristic. What we have taken, whatever the 5 different characteristic we have done. Let me show you back. આજે કરેલું છે same વસ્તુ we have done with the hardware. Number 1, and these are the waveform of hardware. Okay, whether it is tracking or not. So what we have done, અહીંયા તમને PV simulator માં આ value દેખાય. Same value is coming here. So means your algorithm is working very fine. Okay, so this is the partial shading number 1 pattern, number 2 pattern, number 3, number 4 and number 5. So if you see here, we have find out the same value. So it proves that the TPM algorithm is also working perfectly fine in real-time applications too. Correct. Finally, actually in SP5 what we have done, બધા જ PV module ને 1000 watt per meter square નો power આપ્યો. તો 180 watts આવવો જોઈએ. Correct. So that we are getting 179.85. Okay. So this also work in a uniform condition, works in a non-uniform condition, different irradiation pattern, whatever the things. It's work very fine. Then there is one, as I told you, on terrace we have a 6 modules. You can see here, this is 1, 2, 3, 4, 5 and 6 modules are connected. Any upar bhi algorithm run karyu and it harvesting a maximum power point very perfectly. There is not an issue about these things. Correct. So in ultimately we have done a detailed simulation study, experimental validation with a standalone system, with a string, with a PV array and everything. and we propose a new algorithm. We compare with the existing algorithm, and the work is also welcomed by a different bodies. First paper we have published, if you see here, let me show you here, in 2017 in IEEE Photovoltaic Specialist Conference at USA. We represent our particular initial research in this. Then there is another paper we have done, that is a fast computing 3-point model that I explain you in a very reputed journal of USA in a physics area, that is AIP, is a SCI journal. Then we have given accurate expression for single diode model for solar parameterization. This I didn't explain today, that how to find out I0, IL, RS, RSH and ideality factor N with a very less time. That also we have done our research work, but maybe I found that maybe time will be more, so I skipped that portion. So that entire mathematical calculation based paper is presented in this particular journal. Then we have given one novel maximum power point estimation algorithm in a real-time short circuit current in a IEEE conference energy system at Chennai. Okay, we and Giri sir both were together and just give one particular paper on that. The same updated version was presented again in a Scopus journal, that is a renewable energy focus. Another, the final paper I have presented of my full research work in again a IEEE transaction of Journal of Photovoltaics. That is a PV panel performance evaluation via accurate VI polynomial with efficient computation. Okay. So overall, all research you will get in these 6 papers in a very detailed manner, one by one. And yes, our last, this paper number 1 and paper number 5. Basically 5 is number 1 because initially it was presented in 2018 and this is in 2020. It was in a best 50 papers in IEEE General Photovoltaics for 6 months. Okay, till now also this paper number 1 is in a top 50. So people refers more work, so we are happy that people are using our research in their particular research. Maybe it will be helpful for them. Okay, so today just I want to conclude the session with my model, whatever myself and my guide Dr. Ashish Kepanchal has devoted some work to the society, and maybe researcher and industrialists may use that portion. Okay, now if you have any queries related to this, you can ask me, not an issue. So I put a 10 minutes for the question and answer basically. Anybody?
Participants are requested to ask your queries. Just raise your hand.
Any participants?
You may ask your questions, please.
I think everybody understand, or maybe they will do the research and they can contact at any time. You can circulate my email address to them, so sure, I can help you out. Correct?
Sure. So thank you very much, sir, for sharing your expertise with all of us. That you have covered your 3-point model for PV system, then simulation studies, along with the experimental as well as the real-time implementation, and you have explained very nicely. So GC Baruch and on behalf of organizing team are very much thankful to you for accepting our invitation and sharing your expertise. Thank you very much, sir.
Yeah, thank you, Ami. Have a nice day. Shall I sign out?
Yeah, sure, sir.
Thank you very much. Yeah.
Thank you, sir. So thank you all participants. So now we'll be meeting by tomorrow. So tomorrow will be the last day. So participants can leave the meeting.